co-chaired by Dr. A. Professor of Practice from IIT Hyderabad. I request the session chair to kindly take a seat on the dais. And the co-chair is Shri S. Ramesh Kumar, Scientific G, India Bharat. I now invite Dr. A. Venugopal Rao, Adjunct Professor from NIT Warangal and former scientist in Bharat, to kindly introduce the chair.
Very good afternoon, ladies and gentlemen, and dignitaries on the dais and off the dais. It's my privilege to introduce the session chair of this session, Professor Kota Bhanshankar Rao, who is a professor of practice at the Indian Institute of Technology, Hyderabad.
Okay, so I have to thank a lot of people, but particularly I want to just mention that the work I'm presenting is mainly by two of my students, Dasri Mohan and Harihara. Mohan is just finishing his postdoc and going to join Honeywell, and Harihara is already working with Lincoln Electric. So the three case studies I'm presenting will be relevant to the strategic sector, and I've chosen carefully that which has good overlap with ongoing research in labs around here. Okay, so solidification, microstructure evolution, as you know, is the multi-scale and multi-time scale. Satyam has already mentioned that. It also involves several different modeling techniques across. To give you an example, molecular dynamics also should be used for the solidification studies, and one of my students, Ramakrishnan, has done his PhD on that, and so on. So there's a lot to do in solidification, and in additive manufacturing it becomes very important because of the kind of applications that we try. So there are two approaches in the so-called ICME paradigm. The horizontal integration is where the material moves from one shop to another shop, and it's also called as through process modeling. And the other one is called the vertical integration, where you dive down deep into the lens space of physics, which is what I'm going to present today. So what happens is that you have to frame a workflow of various tools. The information is going from one tool to the next tool, scientifically going to be used so that certain criteria are satisfied. For example, you don't want hot tracking. Okay? For example, you want a large window where you could do the heat treatment. So there are certain criteria that you would have, and therefore finally the product can be designed by taking account of all these models. So an example for such is also here as a welding approach. For example, in welding normally, you pick an alloy and you took a process of welding, let's say GTAW or electron beam welding. Straight away you go to microstructure and see whether it's good or not. What I'm saying is, in computational approach, it's a bit long, but digitally done in a very robust manner. You take the alloy, you take the process, model the process, and extract the temperature gradient and cooling rate that are prevalent during the process. Using the so-called phase field approach, you can look at the microstructure evolution. You can then understand how the elements are getting segregated, particularly let's say niobium is segregated in let's say 718 alloy. And then you can look at the microsegregation extent. And then for that segregated alloy, you can actually look at what are the DTT curves that are applicable to see the likelihood of a phase formation such as Laguerre phase. And then from there you can derive what's called the phase map. And the phase map basically is in the processing the parametric space of cooling rate and thermal gradient, where you could see that the gray region is bad news and on the left hand side blue region is good news, and therefore you can design which way you should match the process so that you can avoid the larger space during the welding process. This has been validated with the existing literature in the open literature, and this kind of maps can now be possible because of high throughput computations that are possible due to high performance computing that is available. So some of the things that we have learned from ICME is that experiments should be high throughput. When you do one experiment, you should get multiple data out of that, and then computation should be quick. Okay? Therefore, you should be able to do multiple studies within a limited amount of time. Then there should be a strong coupling between the two. That is, experiments and computation should go together very, very strongly at various levels. Validations have to happen, and then the validations have to be fine-tuned. So these are the lessons that we have learned while implementing the ICME approach for half a dozen processes. Okay, so one example is additive manufacturing of 718 Li. So this is a workflow that we have followed. We have put together a lot of tools that we have passed on the information across, and the outcome is something that is interesting. We have modeled the heat transfer fluid flow process get in the thermal profiles and use the thermal profiles to do the case field simulation and got the segregation, and those segregations are going to be evened out by heat treatment, and then we get into the multi-component diffusion and precipitate formation. So all of this has been done in the computer, and with about 3 iterations, just 3 iterations, we were able to get the best properties for printed alloy. Okay, and we have done that for 2 alloys, aluminate as well as Heinz 22. So precipitation has many complications. All of these are now subject to matter of physical metallurgy. I don't want to go into details. And what we get out is a multi-component alloy can be handled. So we have taken 6 components. So across the world, today actually India holds a record. We have just performed in our consortium group with Abhi Chaudhary and IISc a 10-component alloy, CMS-X4. We have simulated with the phase field approach. Nobody has done that in the world. Okay, and we can do the precipitate calculations to optimize the precipitate size in such a way that we get a very good strength. Okay, and minimize the defects by optimizing the cooling rate and the temperature gradient. And finally, what we get is a high temperature property. Look at the bar charts. The additive manufactured sample without homogenization, but with aging, can give you a slightly better property than a normal plate, that is a wrought alloy of the heat treatment. So you can get better properties of a printed component than a wrought alloy. Okay, but it needs a lot of optimization, which actually is a lot of work that goes behind. So you can do better with additive manufacturing than with wrought alloys. Okay, and we understood, of course, why does it happen, etc. The length scale of segregation is 1/10 that of the cast alloy. 1/10 the lessness means the diffusion times will be 1/100th. So your aging times will be actually done within the ramping up itself. The homogenization is done, and therefore you can skip the homogenization step altogether. Direct aging is possible. But that's a really, you can look at the diffusion profiles, how fast they get evened out. That's the advantage. And therefore, because you are going so fast, the precipitate can be very small, and therefore you get very high strength. So we are able to explain why is it so good. Second example. This is where I want to pass on some amount of pride across. So-called Atmanirbhar Bharat. Microstructure evolution is a high performance computing tool. Okay, it has to have a lot of computation to be done. Okay, you can look at the number of grid points, 10 to the power of 10 grid points, 1 million time steps, 5 LI elements. So it's a massive scale of microstructural calculation that are needed. So it is so large that 10 years back, the world's fastest supercomputing award was given to microstructure evolution. So today HPC is actually microstructurally, it's very important problem, and it requires a bit of computing. And no wonder somebody trained in these kind of computations has won to the winning the same award in 2023. Vishal Subramanian from my group of in IIT at University student. We're very proud about that because very few Indians have won this award. Okay, so this is a tool that we have developed with a consortium of IISc, IIT Hyderabad, IIT Bombay, CDAC Pune, and Sarvik University. And this is a tool that is currently open source. It has taken more than 10 PhD students across all of our institutes. It will take the same amount of effort if anybody else does also. So we decided that let's not have waste of time. We will put all the source codes out in public domain, and we have benchmarked them. All the publications are available, and the benchmark paper is coming out shortly. The website is given here, github.com by ICME India. If you go there, you will pick up the solver. Okay, and this solver has something specific. It actually runs on multiple GPUs. It can handle dozens of GPUs, and it can compute at a petaflop scale. I'm very proud to say that this entire code development has happened in our labs in India, and this is the fastest solver for microstructure evolution in the world. There is nothing like that commercially available even if you want to pay. And this is actually without having to pay. Okay, so this is my coalition partners. I'm happy also to say that one of them is also my student in the past from IIT. Okay, and this, if you check with any computer science faculty or scientists, you will see that we are adopting the latest technologies. We are actually using CUDA and OpenCL as languages for our solver. We are also now developing solvers using what's called SICKLE. So SICKLE is going to be a very big initiative from Intel in the next 3 years or so, because if you write C++ program in SICKLE, you can compile it to run on any GPU. And that's a big advantage. The code development can then be used on multiple platforms. So we are going to have microstructure simulation tools using SICKLE solvers, and the day we launch it, we have one solver already available. The day we launch it, ours will be the first SICKLE-based solver in the world. Okay, what can we do? We can do such fantastic simulations, three-dimensional simulations of complicated multi-component alloys, showing the contours of different compositions, showing you where are the segregations, taking into account gypsums and effect, kinetic effects, etc., and telling you why the nickel compound will form at certain locations and why not, etc. And these can be used to solve by thanks to the phase field models. These models will run across multiple processes, so we slice the grid points and pass on the workload to multiple processes. How many? We have tested for 4,000 cores in IISc. The reason why we did only for 4,000 is because that's the highest capacity in the Parapravega. IISc, Professor Abhi Chaudhary has done that one. And we have tested for 60 GPUs because that's the number of GPUs I have access. But today, shortly, we are going to launch another cluster in IIT Madras, where I am going to lead the effort as chairman of Computer Center. We will test this solver on much bigger scale and show that we are actually scalable. Okay, and it uses very sophisticated OpenCL programming, which I should thank many of my undergraduate students over the years for contributing. And you can get the segregation profiles. We have benchmarked them. The benchmarks are here. The composition profiles are benchmarked, and in 3 dimensions also we are able to benchmark them very well. And what you can learn, because these solvers are very fast, you can actually do a battery of simulations. Okay, 5 by 5, 25 simulations if you do, you can make a map. When you make a map, you can tell for what temperature gradient and what velocity, what is the segregation of my area. And then you can go on to change your processing conditions so that you can get a segregation that you want, or you can avoid it if you don't want. Okay, so by performing a battery of simulations, you can optimize. On the right hand side is a very important insight. Hot cracking. Hot cracking hitherto was given as a label saying that this alloy will do hot cracking, this alloy will not do. What I am saying is that hot cracking depends on microstructure. It depends upon the segregation levels. And you can make a hot cracking prone alloy during additive manufacturing without the cracks. And the processing window can be determined using such maps. So this is an exciting possibility. We have demonstrated that for a welding process on aluminum lithium containing aluminum lithium copper alloy for VSSC, and we are able to show without cracking what can actually be possible. Last one, just very briefly, we can actually develop printable maps also. So I don't want to go into the process, and these images, most of them are very similar to what Mr. Sachin has also shown. Here I want to tell you that the science of what is called a map for printability is more or less well established. Only thing is those lines are not known. Okay? Those lines are not known. So what we have developed is we have captured all the physics of these processing techniques, and we have developed a framework by which those maps can be obtained ab initio. That is, for titanium alloys, we have shown it for BSS in Toronto. That is, we can generate that map for a range of titanium alloys, even though some of those alloys are yet to be made. Okay, we can generate that. And how we are able to do it is because we are able to use machine learning for the property data. Okay, so by using machine learning for property data and capturing all the physics of it, we can actually make a processing map for printable conditions. It is called an AM advisor because it will shrink the number of experiments you should do to have a crack-free print, basically. So if you are going for a new alloy, consider using such a tool so that you can reduce the number of iterations for you to make a crack-free build. Okay, and this is going to save you money and also give you insights about what is happening during this build. So in summary, I would like to say that the National Supercomputing Mission has helped us make our solvers, and we are able to put it in the public domain. I believe it is going to help in ICME because one of the bottlenecks in ICME is microstructure evolution, and today it can be reasonably fast thanks to these solvers. And I encourage, as a professor also, that we should go for open platforms and open source codes because it allows many students to use them and develop their next step. Why should everybody discover everything all over again? And in metallurgy, which is not very common, metallurgy and high performance computing are not talked together in a center generally. But today we can do that. We can take up very challenging problems in metallurgical domain thanks to the HPC availability, and we can also now form a problem that can be solved in a big cluster, not only CFD, not only nuclear calculations, but also microstructure evolution. So that gives me pride because I'm a metallurgist at my heart. So I don't want to waste my opportunity having been given a chance to present in front of INA. Okay, so I have 2 slides for that. One, INA. I want to request INA to consider developing a knowledge graph to capture scientific capabilities and engineering tools in the country. It's necessary. If INA wants to be seen as a society rather a small set of highly distinguished individuals, a society that will actually embrace many more engineers across the country, we need a knowledge graph to capture their capabilities and the tools that they know, etc., so that they can work with each other. And that can be dynamic one, it can be community driven, and I'll be very happy to provide how to go about it because I have some experience in making knowledge graphs. And we need a digital repository of data sets. Enough of publishing only images. We should actually put the data sets out, like Kegel. We should put the data sets out so that the new students who are coming out in the market, they can use those data sets, develop their models, and then take it further by their innovations. And then we need actually an AI-based agent to harness undergraduate research. I am going across colleges for GATE and JEE exam duties, etc. I am seeing that so many youngsters are there, very bright, but their work during BTech projects, MTech projects is just very wasted. We have to find a way to harness that for skill gap and better employability. And I think INA owes them a platform to make that happen. And one last slide about DRDL. I request DRDL to consider INA's roadmap document. Kamak is here. I think it is a very good piece of work, and I think DRDO should take it seriously and go further. Already they are implementing that in one project at DMR lab earlier on. And DRDO should encourage open source codes so that we can have projects where people can contribute to modular code development, and that can be a very good asset for the entire country. I think the approach should be encouraged because I believe it reduces the time scale for development of products. And I believe academics should be given access to HPC clusters in DRDO so that we can demonstrate some of our solvers on your clusters, and then you can take over and start using them for your problems. And that is where Atmanirbhar will come. And now that our solvers are actually also fully developed in India, there is nothing that stops us from them having. Last comment, projects with deliverables like modules which integrate on a platform should be considered because that actually allows you to integrate efforts of across generations. You don't have to reinvent the wheel again and again. Big OEMs like ANSYS, Dassault and all will try to sell you more than what you want to use. Okay, it's about time that we look at open source development with support from academia. So with that, I thank for all of you.
We are now starting our second technical session of the day, which is on processing of powders. This session is being chaired by Dr. R. Krishnan, Director, Defense Metallurgical Research Laboratory, DMR Hyderabad, and is co-chaired by Dr. A. Venugopal Rao, former scientist DMRL and adjunct professor in IT Warangal. I request Sri S. Ramesh Kumar, Scientist G from DMRL, to introduce the session chair.
Good afternoon to all of you. It's my privilege to introduce Dr. R. Krishnan, outstanding scientist, who has taken over as Director DMRL on February 2023. He has obtained his BTech in Metallurgical Engineering from IIT Madras in 91 and his MS in 1992 and PhD in 1998 in Metal Science and Engineering from Carnegie Mellon University, USA. His research interests include the physical metallurgy of high-performance steels and nickel-based superalloys, with a strong emphasis on establishing and understanding the processing, structure property correlations in these important engineering materials. He is also interested in applying modeling and simulation tools to study materials and processes. He has first-hand experience of 25 plus years of working in specialty steels across the entire spectrum from concept to product. His work has been influential in establishing the entire ecosystem, starting from lab scale scientific studies to industrial scale production and certification for final use for the manufacture of specialty steels for naval construction. He has a strong interest in fostering enabling interactions between academia, R&D, and the industry sector towards transitioning concepts to successful products. He has delivered more than 100 keynote invited talks at various R&D institutions, academic industries, government bodies, and conferences. Dr. Krishnan has received the DRDO Agni Award for Excellence in Self-Reliance in 2005, Humboldt Fellowship from Indian Institute of Science in 2010, DRDO National Science Day Orations in Silicon Valley in 2011, and Metallurgist of the Year by Minister of Steel in 2017, and Outstanding Researcher in Academic Institute and R&D Labs Award by Indian Steel Association. With this, I now hand over the session to Dr. R. Krishnan for further proceedings. Thank you.
So good afternoon everyone to this second session of Theme 1, which is Additive Manufacturing for Defense Applications. And the session theme is processing of powders.
Thank you. Good afternoon, and of course, thank the organizers and especially Dr. Jaydeep Joshi and Dr. Masud for pulling me here and then give a talk on this. I know ARCI, all the activities, what we have been doing, and then we have been working with closely with the DRDL. And you all know that the genesis of ARCI, it all started our integrated long-term program with the Government of India and as well as Soviet Union. But the project is actually initiated by DRDL. So we always, it's a product of DRDO, and I'm privileged to stand here in this DRDO complex and then giving a talk on the work what we have been doing. And the topic what we have given is powders for the additive manufacturing and coatings. Because I'll also add on coatings because topic is only additive manufacturing, so I have added coatings because powders, when you do it, some of the fractions of the powders what we develop can be used for the coatings. And yeah, so I mean, we all know that what is the ARCI mandate. It's translational research, especially going into the and then also the human resource development, what we have been talking about. And of course, we have various centers of excellence. We have initially started with the 2-3 divisions under ILTP program. But then over a period of time, we have expanded and then created various divisions to work on energy, laser processing, and solar energy, and then fuel cells, and then so forth. And we keep evolving. I mean, these are the thrust areas, almost ceramic processing, fuel cells, and other things. And then, but what I wanted to say is, because of the paucity of time, I'm not going into the details. We can say that we have done around 47 technology transfers, what we have done, and then provided more than 250 solutions to the industry. When I say the technology, which comes with an IP, when I say with solutions, then there is no IP involved in it. So that's what we have contributed to the industry. And then most of them are defense projects. And what exactly what we do is, any for the technology to go into the deployment, it has to go through a valley of death. And then what ARCI precisely does from this, to say is on one side you have an academic research, fundamental research, what you're doing, and then other side is an industry which has to adopt that. But then there is a large gap. So what ARCI does precisely is to build that gap, and then so that it doesn't die in the valley, but then it will slowly sail off and then take it up to the other side. And that's what we do it mostly on translational research. And then what I'm going to say is we always do it on a pilot scale. Today morning speakers were telling that this is the essence for the making and then the demonstration at the pilot scale. So we have all the capabilities to do it on a pilot scale, and then we do the field trials, and then we generate sufficient numbers to carry out the field trials, and then eventually can be deployed in the market or by the industry. So some examples, latest thing what I'm trying to say is cathode materials for the lithium-ion batteries, which is a lithium-iron phosphate, which we have developed and then transferred this technology both globally and then Indian non-exclusive basis we have transferred. And this company has set up and is being incubated. We also have an incubation center at the ARCI where we can handhold the technology receivers, and so that they mature, they get matured, and then they can go out and then start their own industry. We also do it on another model. What we are doing is on a GOCO model. We can always give our facilities for our technology receivers to use our machines. Because some of them, when they take the technology, we have to mobilize so much of capex, and then where suppose it is looking at only supply to the niche market, then the ROI will be very low. So you will have a very challenge in mobilizing the funds. So for those people, we use our facilities on a GOCO model. So that means government operated, government-owned company operated scheme. And then they can use our facilities and then produce the components and then supply it. That's what we do it, and this is the incubator we have done. And another technology we have done it, of course, with the DRDL. We have developed the tungsten jet vanes with a single-step process by spark plasma sintering. And this is we supplied and then field trials went on, and eventually we transferred this technology. And then other is the tungsten balance, based on this same technology, tungsten balancing plates also we have developed, and then it is completely, all the certification was carried out, and that was done, all the 100 pieces were done on a COCO model by this company. And of course, now coming back, this is the history of that, and then coming back, the whole theme when I'm looking at it is the drivers for the next, technology drivers for the next year. Of course, for the essential, everyone talking about energy, so in materials, energy generation, conversion, and then transport is the one. Then other is, that is not the theme of this forum, but the other ones, lightweight materials processing, which comes in for all the different applications. Then metal additive manufacturing, that's the main theme. Then coatings is another one. Then other more important point is equipment. Even though we have the technologies, but the equipment needed to generate the process, that material or process into that component, still that equipment is not available, still we are importing it. So there is an essence for us to develop the equipment, that indigenous capability we have to develop. And of course, the other one, morning also we are talking about in the keynote lecture, AI and ML plays a very, very important role in the next time. So this is coming to the topic, we have in ARCI, we have a complete ecosystem from the design to the development of the alloys. We have a vacuum induction melting furnace, which is of 10 kilogram capacity. So whatever the alloy we design, we can make that and then convert that into powder. We have an inert gas atomizer, which is of around 10 kilogram capacity. Then from the powder, we have two machines, additive manufacturing. One is the powder bed fusion and another is SNM. Then another one is the e-beam electron beam melting process, two equipment we have. Then we also have a post-processing equipment like hot isostatic pressing or the vacuum furnaces, high temperature furnaces. And also we have developed, other essence is the surface. When you build with AM, obviously the surface roughness is not as smooth. So we need to have a surface treatment. So we have developed the post-processing to improve the surface roughness. And so that's a complete ecosystem we have been working on. We have established at ARCI and a demonstration pilot scale levels. And of course, when you say that powders, you can always looking at there are many systems. You can say that powder bed fusion, then direct energy deposition, or material jetting, or binder jetting, or polymerization, metal extrusion. So all those things they need powders. So various different companies they make powders in the world. And of course, the powder manufacturing requirement world keeps increasing because you all know that AM is going to have a lot of use by many people. So that's why the continues to increase. 2025, we see that a lot of around 2,000 million euros. So that's going to be a very big amount just for the powder. That's a trend which is going on. Then, when we coming back to that powders play, morning also in the talks we have seen that powders play very important role in defining the final component capability in terms of its soundness. I can say that soundness in terms of its porosity, density, and the defects what we have. So we have a different powders, when you are manufacturing by the gas atom, because you need to have a spherical powder. So gas atomization is the one which you use. Everyone is using that, very widely used. And when you make that, you can ideally you have to make a spherical powder. But then if you don't control the parameters, and then if you don't do the, sometimes you end up with the other kind of lot of satellites, and then elongated powders, then also sometimes porous powders. The other thing you can see the broken particles. So all those, you end up with all those things if you don't control it. But essentially is, how do you control that powder to get a near-net shaped, a spherical shape without any defects, without any satellite particles, without any pores. So that's a challenge. And of course, what is going to happen? Then another question is, you need to use a particular size distribution for a particular So you cannot use a very wide, whatever I get it from my powder unit, powder production unit, I cannot use it. So what is happening is generally depends upon the flowability, uniformity in powder bed density and packing of powder between the layers. So that's very, very critical. Then image based and non-image based techniques we can work out what would be the size and all. So then it can be have a good pack density. You all know that in a powder metallurgy thing, if you look at it, if you have a bimodal distribution, you will get a good pack density, and then so that you can also get a good density in the final components. And then essentially what happens is the pores. Sometimes you end up with the bottom pores if you use a particles like that. Then you also end up with the pores and a lot of defects in the component what we see. So essentially you have to play with all these things, you have to take care to get a very good soundness of the AM printed components. Whatever may be the material, whether it is a simple iron or it can be stainless steel or it can be supervised or it can be any other fancy material like GRX and then NASA is using it. So what we have done in ARCI, we have seen that the top portion of the 5 alloys, nickel based superalloy 7monite at 625. Then we also done the modified 7monite, then BZL 12 by the Russian grade alloy, and then aluminum alloy 7050, which is not AM friendly, but then what we have designed that composition, tweaked in with the alloy. The morning lecture we have seen that we have to tweak it. So then we have produced the powders and then printed it and then made it in AM friendly. And then other commercial powders, what we are doing essentially tool steel, stainless steels, EH steels, aluminum alloys, copper alloys, magnetic materials, even NDAP we also printed. So what I wanted to say is over a period of time, ARCI has developed that kind of an expertise and then they have finalized that all the process mapping for each material. So for the printing, to get a good density of the components. And this is what I was talking about, the bottom pictures, if you see that, this is called the GRX. This is nothing but an oxide dispersion strengthened superalloy, which is made by the NASA. Generally dispersion, they have done it, so they have done the dispersion. Till now the literature says that you have to put in a lot of high energy ball milling and to disperse the oxide particles very uniformly in the particles. But when you are doing that high energy milling, then the particles from the spherical, when they become irregular shape, then they have, they lose, and then they will not be compatible for the additive printing, AM printing. Then what they have done is they devised a technique so that the oxide particles are distributed without changing the morphology of the spherical powder, and they have printed all these components, and then these are all testified. So we are also working on some dispersion strengthened materials, especially oxides, without changing the morphology of that. Then, what I wanted to go through that is the process, inert gas particle process. Ultimately, my aim is to get very good shaped spherical particles, as minimum as satellite particles, and then with a uniform particle size distribution, very, very narrow particle size distribution. But that is very challenging. And what happens is, again, those kind of things depends upon the parameters, the vacuum levels in the system, type of gas and gas flow rate, what we use it for the atomization, and then extent of superheat, what we give it, and then metal flow rate. Then particle size varies with that, the gas to metal flow ratios. So we have to control all those things and then to get a very narrow size and then good spherical particles. So this is what it happens. The molten steel, the molten metal. Initially, you have a ingots or whatever may be the metal. You take it, then you melt it, then you take it to the superheat, then you allow that pass through the nozzle. Then you have 2-3 different types of gas jets which coming in, which is essentially one kind of the other one. This the grey colors, the outside ones essentially define the size of the particle what we are getting it, but the inner gas jets, which are used essentially to remove any solidified particles sticking onto the nozzles. What happens is for a period of time, if it is not knocked out, then they will block the nozzle and then they will not allow the metal to flow, and then you have to abandon the atomization run. So you have to be, this is another crux, you have to design this die and that plays a very, very important role in defining the particle size. So we have the system, that's what 10 kilograms of melt capacity. You can use helium, nitrogen and argon, and it's got a vacuum induction furnace on the top, then automation in the middle, and then the bottom one is a powder collector. And over a period of time, we have generated a data that's a gas pressure, gas to metal flow rate with a medium particle size. So we can say that whatever may be the material, then we play with these G by M ratios and then to get that particle size what we need. Yeah, so then when we are doing that, we also have an vacuum induction melting, so we can make all this alloys which are designed by us. Otherwise, normal conventional alloys, we buy it and then we do it. Of course, most of the alloys supplied by Vidani. And then these ingots are the feedstock to my atomizer. And typical morphologies of the powders, what we get it is 9 chrome, iron, aluminum, chromium, 18 chrome or iron 718 powders. We get this. You can see that very clean, very less satellite particles. Then 718 alloy powder we have developed and then we have printed with an additive manufacturing. And what I could see is we can always get a composition. You can see that the composition is from the commercial to our atomized, there is more or less similar. There is not much deviation. So another advantage, another challenge in the atomization is the loss of the metals. So if you are looking at a low vapor pressure materials, then they tend to vaporize when you are heating up, and then essentially what is the composition of the ingot what you are putting in, and then you don't end up with the same composition. So you have to take care of that kind of things, and then you also play with the positive pressures what you have taken. Then what I am trying to say is we can always see that all the materials will get a good density and compared to the commercial material. So we could able to get a good suitable material compared to the commercial ones. So this we have done it and then validated. Yeah, okay. Thank you. I'll finish it. Then other one is 6 to 5. We have done it. Then here also same thing. From the ingot, the powder, the AM, we have done, and we get a very good density, 8.37, comparable to the conventional density what we get it. And then typically I'm looking at it is the oxygen content is only 100 ppm or 120 ppm what we get. So our systems are very, very rugged, and we also see that there is no oxygen ingression or oxygen pickup during the atomization. So if you don't maintain, that's also another important factor. You have to control the oxygen ingression into the powder when you are optimizing. Then we also made talking about iron manganese. So this is another difficult system. So you have around 35% manganese, and that maintaining that ratio 35% because manganese evaporates very fast, and then maintaining that kind of a concentration both for the powder making and then as well as for the additive manufacturing is a big challenge. And we have overcome all those things. Typically, we look at it, the particle size, we screen it, and the yield, what we get, for an AM SLM, we want to get around 25 to 58 microns is the size range, and then peak is around 40 microns. That's a powder what you get it. But you also end up with higher coarse fractions also. So you have to sieve it, and then what our experience is, we get around 60% of this fraction. What are we getting it as suitable to the AM? And then the coarse ones, what can be fed into our E-beam, electron beam melting, because they need plus 70 microns to minus 150 microns. And the still final powders can be used for coatings, cold spray coatings. So here we have treated it, and then crack free, we had initially a lot of challenges in getting cracks and then all those things, but we could able to make crack free materials, printed various coupons for the tensile properties and also for the corrosion, but this is meant for the biodegradable implants. This is a soft tissue anchor, the last one, which is all able to do it. So the other the bottom right picture gives you the actual soft tissue anchor on a support plate. That's what we have And generally, as produced, you get very wide range. Then when you screen it, then you will all get it into that kind of size. We are also working on our people, AM scientists, Gururaj and Manish, they are also here. And they are also working on optimize the process parameters to have a wide particle size distribution, so that we can have a maximum powder can be converted and then can be printed into additive manufacturing. Yeah, this is another one BZL 12 by Russian grade alloys, and then we took those components and then atomized, produced the powders. So here we had a challenge. So there are so many elements, and then we had a challenge in controlling it. So the particles are not as neat as the powders what I showed you earlier. But then we have sieved those powders, and then we could able to get 11 to 57 microns of that size, and we could able to print it. But then we end up with all this solidification cracking. So this is a very case where we have to now optimize the compositions to remove that solidification crackings, or otherwise you have to play with these parameters of the preheating or any other things to avoid that kind of fast cooling rates, so that they don't crack. So still we are working on it. Then this is another one. We are talking about an aluminum alloys. Only ALSI is only printed now. That's all. Then 7050 and then other alloys are not AM ready. And this we have altered this composition. And then with our design, with our Greenhouse CSM and one of the projects, international projects, what we have done, and they gave us composition complete design, and we have optimized it. Then we made the ingots by using our vacuum induction melting. Then we produced the powders. Then we have printed it using our SLM machine, and we could able to see that printing things. We could able to not completely avoid the cracks, but then there are still some micro cracks. Still work is going on, so that we can tweak in those. This essentially it contains zinc. So maintaining zinc within that range is also another challenge. So when you are trying to heat up and then atomization, there will be a lot of loss of zinc. And then even with a little bit tinkering with the zinc composition, then you end up with the solidification cracking. Then of course, I will just quickly run through that. Some of the powders we use for the thermal spray coating. So what we have done, our powders. So these are all, everyone knows that various kinds of powders, nickel chrome chromic carbide or tungsten carbide cobalt powders, or M-Trolley, Co-Trolley for the bond coat powder. So we have been, this will very widely used, and then most of the powders are supplied by these three companies, Fraxair, SC Stock or Polycon Menco. So we don't have the capability to produce those powders. So we have also started making those powders for the coatings, because this also I told you, like additive manufacturing, for the coatings also we have a complete ecosystem for making the powders and then try with the coating techniques and then validate, benchmark with the commercial powders, and then we can qualify the powders for the coatings. So that we are working towards establishing that capacity building for the powder manufacturing in India. And one of the powders what we have done is iron aluminate powders. We don't see them because new composition we are developing it, and then we have done the coatings powders. Yeah, 1 minute. 1 minute, just finishing things. I'll just go through that. Then we compared with the nickel chrome chromium carbide material, and then you can always see that they are all comparable on the right red pillars. If you look at it, they are all comparable. And yeah, even here also, here it's a very low compared to the nickel chrome chromium carbide things. So this can be deployed. We are working with that for the field trials. This composition, we are working on it. And then other powders, FEAL, we have done. So here you could see that very wide particle size distribution we could able to get it. If you don't change, you can also see that very disturbing the morphology of the powder body. One of that. Yeah, this is another powder, again FEAL ZR, we have produced it. Then, of course, the new techniques which are what I told you is inert gas atomization, but we have a new technique which is also coming up as a plasma spheroidization. I think DMR Then other is the one ultrasonic atomization technology. Unlike gas atomization, the molten metal is put it on a very high frequency plate and then it vibrates, and then you will always get into the very fine powders of uniform things. And this is another thing. So these are all the things. What I'm trying to say is that what we need to have is we need to have an infrastructure completely to produce all kinds of powders of all kinds of sizes, what we need. And because the inert gas atomization only can produce steel, superalloys, aluminum alloy powders, so they don't do the other titanium alloy powders or the even high temperature alloys. And also the other point, as mentioned by my earlier speakers, feedstock for the powder manufacturing. So that is also a very, very important thing. We should have the capability to produce as clean as, because if you don't produce a clean ingot, then you end up with a very unclean powders. Then the new powders, there is also need for developing new powders. One is the niobium alloy powder, which is NASA is already using this niobium alloy, or new ODS superalloys, which is called the GRX, the trade name. So that's the kind of powders we need to develop. Then of course tungsten powders we need to do it, and then tungsten additive manufacturing also to be done. And high entropy alloys, that's a new class of materials which are coming up, and then we should produce those powders for high entropy alloys. And of course I mentioned dispersion techniques. Yeah. So what I'm trying to say is additive manufacturing and coating. So we have complete ecosystem at ARCI for development of powders to the printing or the coating, and then validation, and then benchmarking. All the facilities we have, and then we also have these facilities are at a demo scale, at a pilot scale. So easily it can be field trial, can be done with the field trials, and then easily adaptable by an industry. And finally, ARCI is open for collaboration with industry, R&D, and academia to raise new technologies, innovations, and commercial success in the field of particulate materials-based technologies. Thank you very much.
Thank you, Chairman and Co-Chair, for introducing me to the audience. And I also would like to thank the organizing committee to give an opportunity to share my experience, because I have been there with DMR and DRDL on the subject given to me, plasma rotating electrode process powders for additive manufacturing. To that, I have little bit added strategic material sustainability. Previous lectures I was not there, but 2-3 lectures including many things we taught. Anything we design, anything we talk, we can talk. But where is the sustainability? For example, DRDO works for the nation, IME also works for the nation with international reputation. But there are 3 important things. Number 1, economy, environment, and society. With all these things together, we can work for the development of the nation. And within this model, there is one important space for us, materials people. We are the materials people, and we develop the materials. What we have to look into it, when a superalloy composition has to be established, we should not only think that what is the volume fraction of the gamma prime, solvent temperature of the volume prime, or working temperature, turbine inlet temperature. What are the ores available? Do we have a niobium? Do we have a hafnium? Do we have a cobalt? That also has to be considered. You take America, France, Russia, and China. You take France, SNACMA, they developed American alloy. They have removed niobium, hafnium, reduced it substantially. They have considered molybdenum because they have plenty of molybdenum. Likewise, United States, Inconel 718, they have introduced cobalt because they have availability. And China, FGH 95, high strength nickel-based superalloy. They are not dependent on any alloying elements, they are dependent on the grain size refinement and achieve the fatigue resistance combined these materials. So these are the considerations when we develop the materials or use the material, develop the processes. We have to have a linkage, what is available, what is not available to meet the ultimate requirements. However, Indians are very clever and we have launched ICME programs, modeling, simulation and all. We have the DMR, we have the test of modeling, how it will help, how it will reduce the effort and time, all that. Modeling and design innovation, life prediction and extension concepts, rejuvenation and refurbishment, materials recycling technology and alternate material solutions. Just now someone talking about this C103. Where is an off-year? Off-year will not there. If you stick to off-year with the same composition, then we will develop the C103. Tungsten heavy alloys for anti-tank projectiles. Almost 90% tungsten is there. In the earth crust, 0.03 to 28% only maximum WO3. Wolframite is available. If I want to always think the tungsten development using the tungsten is the basis, it is difficult. So that is the thing. We have to have a mindset. What is available, what is not available, and all that. Judiciously we have to use the materials. That is what sustainability. Now, processes. I am a processing person, spent so many years at DMR, traditional melting, casting, hot extrusion, forging and all the traditional things, but the traditional processing technology have a limitation confined to certain compositions. Including 718, low volume production, easily processed. You can forging, rolling, extrusion, everything can be done. But can anybody do? Recently DMR has developed 5 new alloy compositions. Can anybody handle it? Can anybody process it? Very, very difficult. So therefore, advanced technologies within this and powder metal, many things are there. But today's context, I would like to emphasize isostatic testing and additive manufacturing. So they are the very important things. Now, under the processing, investment casting. In the South Indian regions, we just look at it, leave it. But you see the complexity, how the pattern is developed, how the fine features of the complexity, and it is a classic example of near net shape capability of investment casting. Today, from this, statue to, we are going up to turbine plane, auto turbine plane for efficient aero engines. But the investment casting also has a limitation. At the maximum 6 to 7 kg components, we can make with complex steel. But can anybody make investment casting? Use the turbine disc of 100 to 120 kilos for advanced AMCA type of engines? No. So this process is failed. Therefore, powder metallurgy, fine powders are very, very important. Why they are very important? See the cooling rates. 1 degree to 100 degree K per second as compared to a fine powder particle which is produced by atomization or plasma-rotating electron process. But that matter any other techniques of similar kind, they will give 1000 to 1 lakh degree Kelvin per second. So the cooling rates are substantially high. Any number of elements, you will be able to overcome the segregation problem. Then use the fine powder which represents the large size ingrat, but size is small, but composition is highly homogeneous. You will end up with a homogeneous microstructure, consistent mechanical properties with excellent workability. So that is the advantage of powder metallurgy, powders. Therefore, we are talking about today how to make the powders, high quality powders and all that. Now, it is not that today we are only talking electrolytic processes, powder making, copper and all that, and that at 1950s. From 1950s to 1970s, all over the world they looked for the pre-alloy powders. At that time, DMR also, DRDL also, on par with the international countries, they have started working on the development of pre-alloy powders. Consolidation of powders by solid state technique like hot isostatic pressing, the visionary, that V.S. Arunachalam sir introduced this technology to India in 1979. From there, DMR, of course, I'm from DMR, I have to, whatever I have learned from there, I will confine to that, the alloy steels, nickel-based alloys produced by atomization, plasma rotating electrode process, EP741 and PIP695 titanium alloys. All these materials dealt and established structure property correlations and wide range of components for small engines like missiles, space vehicles were developed, and whatever the vision they have, all that have been met, and all this information will be made available in 2 articles in 2 different volumes of Defense Science Journal. One is in 2012 and another is 2023. Okay, having got this experience, what further we are looking for? Now the question is additive manufacturing. Additive manufacturing, there are so many techniques. Each technique requires a different size fractions, different kind of powders. But all the techniques requires, some techniques are available for dealing with the material metals, some of them ceramics, some of them polymers. But today I am confined to metallic materials, superalloys and all that. Okay. Variety of components are produced. Some of them for commercial applications, biomedical applications, aeronautical applications, space applications, niobium alloys and all that. But with the development of additive manufacturing, the demand also increased for the producing quality powders. So, the laser powder that fusion alone will have so many parameters. Each parameter will have some influence on the initial powder particle. Then finally, the powder only decides the quality of the final product. Several researchers, what they say that is, when we make an additive manufacturing rule for fabricating a particular component, what first we should mind is individual powder particle. Forget about the bulk powder like this, only individual powder particle. Does it have a satellites? What kind of microstructure? Is it cellular structure? Is it dendritic or cellular combination of dendritic? From which cooling rate it has been developed? All that first one single powder particle one has to look into it. Then bulk powder particle comes in. Does it have an intraparticle porosity? Once the powder has intraparticle porosity by any means, particularly the nut shape technologies like additive manufacturing. Subsequently, we are not going to adopt any thermomechanical working to improve or change that shape. If that is the case, the powder should be totally free from intraparticle porosity. Then the bulk powder characteristics. Bulk powder characteristics, just now Dr. Vijay told that by manipulating the atomization parameter or some operating parameters, we can change the median particle size and size distribution. So I made a comparison. Typically, atomized powders will have the second column if that properties, but if the same powder is produced by plasma rotating electrode process, you can see here the oxygen content will be very, very less. Because plasma rotating electrode process doesn't use much volume of gas. It will use 9:1. 9 is helium, 1 is argon. So when the gas content, insoluble gas content is decreasing, automatically the oxygen levels in the final powder will be reduced. That tap density is a consistent tap density. When we measure the tap density by Hall flow meter or tap density meter, we don't have the jolt. The plasma rotating electrode process powder, once you fill it, it's perfect. We don't have to use any jolters. That will help in making a complex shape components in a single step. That is what is called direct dipping, powder to final shape, or additive manufacturing. Some examples I will show you little later. And the flow rate. Generally, we powder metallurgy people, when we buy powder or sell the powder, we say that if the flow rate is less than 20 seconds per 50 grams, oh, it is very good powder. But you see the 13 seconds per 50 grams. So that is the major advantage of plasma rotating electrode process powders. Of course, these aspects Dr. Vijay has already told this size effect. When we use the fine powder, we will end up with the fine grain size material. When we use the coarse powder, we will end up with the coarse grains. Coarse grains are very good for grip, but see, internal defects are there. That is what is called thermally induced porosity. That comes from the powder stage. That we cannot eliminate. Only thermomechanical working is only the solution. If we adopt by consolidation followed by thermomechanical, we we are losing the nut shape or near nut shape advantage of any process. And when we want to make a sharp blade profiles and all that, too much coarse or too much fine also won't be good. There should be a size distribution. Two different size distributions I have shown here. Atomized powder will have a wider particle size distribution that will have its own advantages, but wider particle size distribution, more surface area, more oxidation prone characteristics will be there. But plasma rotating electrode process will have a narrow particle size distribution that is good for the uniform grain size and consistency. Then what are the spherical shape powder manufacturing techniques available in the world? Atomization, anyway, small atomizer in 1983 itself, DRDL has its own design and established the atomizer plants, produced the powder, amenable to hot isostatic pressure. Then electrode inert gas atomization, ALD has come up with a new concept, and rotating electrode process, but rotating electrode process will give you the tungsten contamination to avoid the plasma rotating electrode process has come. That is by United States, but the Russians and some of the French people, they use the plasma rotating electrode process and similar other techniques. But when we compare all the techniques, which one is the prominent, which is more powerful, which can give the high quality powder in that plasma rotating electrode process, you can see productivity and powder morphology and oxygen levels, everything is far better than any other process. Now what is plasma rotating electrode process? The material to be converted into powder form is taken as an anode, and one end of this anode is melted by plasma torch, and the anode will be rotating at high speed, typically 15 to 25,000 RPM. When the molten metal film forms on the one end, the film comes out due to centrifugal force, and when the centrifugal force pulls out the molten droplet, the surface tension also opposes, and when the equilibrium arises, the molten droplet takes a spherical shape. By the time the molten droplet comes out and reaches the tank bottom, then this becomes perfectly solid. So the molten droplet comes out like a cricket ball, like a spin. With spin, how it comes, then this becomes a perfectly spherical powder, and it is called container-less process because the molten metal does not come in contact with any ceramic containers or any other containers for that matter. That is the reason this material, this technique is adopted for titanium because it's a highly corrosive nature. So plasma rotating electrode process is best suited for titanium alloy and all that. Okay. Now you can see here the morphology, perfect spherical. In fact, this powder we have obtained from Brest, Moscow, Russia. And the cross section you see, we take number of feet, the intra-particle porosity is not existing here. And when we subjected to hot isostatic, this is the formula how this is related D50 with the rotational speed and electrode diameter and material transfer and all that. When compare closely the atomization and plasma rotating electrode process, the atomized powders will have acetylates and intraparticle porosity. The intraparticle porosity is not at all acceptable. When we subjected to the plasma rotating electrode process by hot isostatic pressure, the microstructure will be fully equiax. It is as good as a forged material. But because of the high oxygen levels and all that, the IgA powder, inert gas atomized powder followed by hot isostatic pressure will give you the prior particle boundaries, which will impair the metallurgical bonding between particle to particle that will lead to inferior creep and inferior fatigue properties. So these are the drawbacks. And it's not that just we, in 2-3 minutes I will cover. It's not that just we rotate and we achieve the required quality. Rotational speed is important. Material composition also very, very important to overcome the presence of intraparticle porosity. In the plasma rotating electrode process, varieties are there. But basically one is the short bar. Short bar technique, we can use something like 3.5 inch diameter to 10 inch length for experimental quantities production of powders. But when we want to scale up version large quantities, we can go for a long bar method where the electrode can move back and forth and at a time up to 2000 millimeter length rods, electrodes can be loaded, okay, and large quantities can be produced. A typical heat system, the prep system look like this, and it can be used, as I was mentioning, titanium alloys, nickel-based superalloy alloy steels, refractory metals and aluminates. And the electrode preparation, the technology has not been disclosed anyway. Okay, generally the cast ingots will have a tapering, but electrode is a cylindrical all along its length. Then how it has to be cast and all that, we made some attempts at DMRL, and titanium alloys also we processed through hot isostatic pressing. Then there is an apprehension when the electrode is rotating at 25,000, and these days new mechanisms, new motors and all they have developed. The electrode is rotated up to 40,000 RPM to meet the fine powder requirement as far as the additive manufacturing is concerned. If that is the case, when electrode is rotates at a high speed, if it breaks some because of the presence of some defect, what happens? This is the non-scientific way of fear in the mind. But one of our directors at that time given a task, you calculate what would be the defect, what is the stress experienced by the electrode. So we have taken some mechanical engineers, all 2-3 people put together, we made a calculations. You see here that right hand side, initially the stress levels will be very high, but when the speed increases for all the diameters, the stress imposed on the electrode is very thin, not more than 1 megapascal. You take any cast soap alloy, the strength is far better actually. It's much higher. So that fear one need not have. However, the electrodes preparation is still surface fit and all, which I will. Then, having known the significance of what other countries have done, Russia has adopted and they have developed the large size combined discs for aeronautical applications, and several engines MiG-29 and all that I have given there. And SECMA, France also they use titanium alloy powder for their space programs, and the cost 50% of cost benefit is there because powder to final shape. In between we are not wasting by machining or anything like that, forging and all that it is avoided. Then if that is the case, what India has done, in particular DRDL, having known this fact, DMRL also purchased the powder at the time we haven't had, and this is a integral turbine rotor required for GS service in cryo engine of geostationary satellite launch vehicle. We can see here there is a blank from EP741 and PIP698P. Okay, the shaft will see cryo temperatures, disc will see high temperatures. They were making combined blank, and the blank were machined by electrochemical milling to realize the shroud, blade, disc and shaft in one go. But at one point of time, Russia denied to give these components to ISRO. Then the problem was referred to DMRL, then we started to resolve this issue. Then we thought prep powder is the only thing because it has a good cap density, flowability, and the materials what they need we have taken and designed the capsules and all that in one go. The shroud and the blade and the disc and shaft in one go we could develop by using the plasma rotating electrode process because of their excellent cap density, flowability and all that. Then as on date, the advancements have come, requirements have come as far as the additive manufacturing method. Worldwide, people manufacturing up to 40,000 RPM for the AM purposes. And the electrode, I was telling the details are not disclosed, but we can gather from literature. So these are the electrode straightness and all that. And operating environment, productivity, and feed. At a time, 100 electrodes can be loaded. Okay, like pistol, how that bullet, loaded at a time and it can be fired. Same way, prep electrodes can be fed and one after the other. Thumbs level we can produce. That is the product. And another important thing, all inert handling. Once we have the prep powder, it's not that. See, Russians, how they maintain the capsule containment as good as a capsule for keeping. And oxygen absorption, we will have a wrong notions. Today no problem, tomorrow also 2-3 days, 1 week also no problem. But if the oxygen content to begin with is very low, in a 1-2 days it becomes oxygen becomes 120 ppm. Once it is saturated, there is no point, it will remain as it is. So these are some facts, scientifically we must know. Then why we all the time low oxygen content, low oxygen content? You can see 3 different oxygen content powders in the artificial breast and evaluate you can see the material prepared from high oxygen material powder will lose its ductility even at 200 degrees Celsius. That is the reason we have to have a low oxygen content powder. And degassing, absorbed oxygen degassing also, there should be a scientific basis. Mainly the super alloy powders get degassed at 400 to 500 degrees Celsius. So these are the parameters. Then powder cleanliness. If fatigue crack initiates from the enclosures, then how to avoid sieving, how to remove the metallic and non-inclusion, the equipment available today. And another thing is finally, this is the final slide. It's an atomized powder, directly we pick prior particle boundaries comes. Strength is good, but activity is poor. If this material process through powder bed fusion, there are also problems, internal porosity. So it requires subsequent heating, so this becomes a rot material kind of microstructure. So post-heat treatment is also very important. That is the very important point I would like to have. So with this, my opinion, the additive manufacturing is a fast-growing technology, manufacture of complex components and wide range of materials for application in defense-based nuclear and petrochemical industries and biomedical as well. To enhance the quality of AM products, the design of alloy composition, high quality powders and process optimization, including the post-printing treatments are highly essential. Therefore, a dedicated research activities in the fields are to be seriously pursued and encouraged. Plasma rotating electrode process has substantial potential for yielding high quality powders of titanium and other materials, refractory and aluminides, etc. For additive manufacturing, a wide range of components with reliable performance. Prep is not available as on date, despite efforts made by like DMR and Vedani and all. But due to some genuine reasons, we could not establish the technology as on date. But still, there is a constant endeavor towards acquiring this facility. The technical know-how of prep is kept confidential by foreign institutions manufacturing. To mitigate this problem, government involvement is needed. Just making a procurement case and leaving it to that, and we may not be able to succeed. Therefore, the government authorities' involvement is very, very important. But in parallel, an indigenous R&D program can be launched with the involvement of expertise groups for the design and development of prep using modeling, ICME concept. So then this will definitely ensure production of high quality powders to cater to the needs of AM, heating, etc. to accomplish self-reliance in the manufacturing sector. So because I spent so much of time in DRDO, I convey my gratitude to all the administrators, including the secretaries, the present one, Dr. Kamath sir, the directors, the present one, Dr. Balamurali Krishnan sir is here, Dr. Madhusudan Reddy sir, and DGs, and scientists, officers and staff of DMRL. We used to like a military, I used to say that we cannot become a scientist, we become a soldier in the battlefield. So that was the spirit we had, we enjoyed. And today morning also there was I was not well when I went to doctor, there is no medicine for you, you have to suffer with this and all that. But when I went after 6 months to DMRL, the group where I had a very good medicine, and at that time very much active, that exponential development, silicon nitride granules, complex material, they made, my colleagues, my team, Director DMRL was there. I really felt it. This is the best medicine. So I felt it. So it is a team spirit, it's going on, and that's why I'm very, very happy. Then finally, though it's a very new organization, the Vice Chancellor of the University of Hyderabad, Professor Basudkar Jagadeshwar Rao, and my dean first. Okay, with their consideration today, I am able to come here. I am with you. Thank you so much. Thank you for your consideration.
I would like to thank the organizing committee for giving opportunity, like industrial partners like Indomet, because most of the lectures are from the research academics. And so I would like to explain here about the emerging trends in powder processing. Most of them have already talked about the laser powder bed fusion or EPM, or we can say the beam-based additive manufacturing. So today I would like to talk about beam-based or sinter-based additive manufacturing, especially biological 3D printing and lithography-based manufacturing is relevant. And a little bit on the powder production methods, what is happening, and how we are working at Indomet on optimizing the powders for biological 3D printing. So everyone aware about the different additive manufacturing processes being used depending upon the type of raw material used, like paste on powder, wire, feed, and sheet. Here we are going to focus more on the powder-based systems, like one is the powder bed, powder feed, and powder spray type systems, and mainly the powder bed systems are more popular, mostly using the laser electron beam. And today what we are going to discuss is mainly on the bonded using polymeric binders like binder jet 3D printing. So again, just to differentiate between different additive manufacturing processes, considering the beam-based and beam-less, and apart from the beam-based, beam-less additive manufacturing processes are also becoming more popular. Mostly the binder jetting, sports spray additive manufacturing, and other the additive manufacturing processes. So based upon the depending upon what is the different bonding mechanisms for the beam-less additive manufacturing process, there are different bonding mechanisms are there, like material melting, bulk severing, then electrochemical methods and thermomechanical methods. So the sinter-based additive manufacturing, like binder jet 3D printing, material extrusion, then 3D screen printing are also being quite a lot used in industry. And main advantage for these beam-based additive manufacturing processes are like low energy consumption. You can achieve much higher dimensional accuracy and can be used for printing the parts from micro size to the mega scale. Like from EFAB, we can go for micro scale to the CSM, like we can go to the mega scale. And also you have more material options. So it can be used from many materials like metals, ceramics, ceramides, or any other material which is available in powder form and can be sintered or can be processed. So there are like again to how the different beam-less manufacturing methods depending upon the part size and the part complexity, how it has been divided. Like as I mentioned, like the cold spray manufacturing process, you can make a very big parts. Whether you can make a very fine micro parts with the 3D assemblies with the electrochemical fabrication EFAB methods. And in between, binder jetting is the one of the technology which can be used from the small to medium scale components with quite a good complexity. Again, on the number of parts, like most of the additive manufacturing process, like we stick to the very small numbers or the prototyping or small scale manufacturing. But nowadays, you can go for high scale manufacturing as well, using the beam-less additive manufacturing processes. And depending upon the part size features, like you can go for like few microns to the quite a bigger size components, right from EFAB to the cold spray manufacturing methods. So there is a very this beam-less manufacturing methods are very we can say they are more flexible in terms of materials, sizes, as well as the features. So you can use it in a wide variety of applications, not restricted to any particular material, particular size, and particular these feature sizes as well. So this is a study published in the Overall's report comparing the systems installed in the industry, with the beam, using the beam and the beamless. So now you can see the beamless manufacturing methods are catching up with the beam manufacturing these systems. So there are a lot of the companies in the industry are adopting now beamless manufacturing methods as against the conventional beam manufacturing methods. So today I am going to explain about the technology which we practice at Indoga, this metal binder jet 3D printing. So this is as I mentioned, this is sinter-based additive manufacturing. So again, the raw material is the feedstock is the very fine powders typically used from the gas atomization, and there is a binder jet 3D printing process. I will explain you what is that. After that, you get a green component, like how you get in a powder metallurgy, like green component, what you call. Then it goes through the subsequent processing of debinding and sintering. And sintering is the final process which gives the final shape and the material properties to the component. So in the right side, what you are able to see a typical schematic of typical binder jet system, which is very similar to your laser bed fusion system. Instead of the laser optics, there is an you have an you can say the mechanism like or normal printers how you have printed. So similar printhead which injects the binder onto the component. So instead of a laser or the EPM, you use the binder spray to coat the metal powder layer by layer, so that you are actually gluing the powders layer by layer in the binders. So you are creating a green component, and that green component, once you have completed the printing, you remove the binders by debinding process. It can be a solvent debinding or a thermal debinding, and subsequently you sinter the material like powder metallurgy component into a almost full density material. So as I mentioned, the process starts with spreading of the powder layer, then the checking of the binder to glue the required area into the metal powder layer, then the curing of the binder, because these binders are need to be cured to get the strength of the component. After the curing, you depowder it, like the remaining the loose powder has been depowdered similar to your laser bed fusion materials, and then after the depowdering, you do the debinding and sintering and post-processing operations like dipping and heat treatment, typically what you do for the cast of the hot materials. So you can see here that you can make a very complex near-net shaped components, and also because it's a sinter-based technology, you have not limited to like low carbon materials or the materials which is not prone to crack during welding, which is the one of the major limitations for the powder bed fusion techniques. Here you can go for ceramics, you can go for cements, like we have made some of the tungsten carbide materials, ceramic materials, different tool steel material like M2, which is going to talk about that, like very high carbon materials. Name any material, you can process it this through technology. And almost depending upon how you choose the material composition, particle size distribution, and the sintering the profile, you can get close to 99% of the theoretical density. Even with the heating, you can go close to 100% density. And also the major advantage what we get it here is a good tolerance. The tolerance typically we can get 1 to 2% of the nominal dimension. Sometimes in the best practices we can get as close as plus or minus 1%. So we get almost close to the near signature component and good surface finish. You can get almost 3 to 5 micron RA surface finish against the much coarser or the much rougher surface what you get typically the powder bed fusion the technologies. And also the minimum features, like you can make a very intricate features like as close as 0.7 millimeter features also we can make it with this technology. So we apart from the component manufacturing, this technology is very much popular for making the conformal mold inserts. These mold inserts can be used for plastic injection molding, metal injection molding, die casting, hot forging, where the conventional manufacturing, like the laser bed fusion, the maraging steel is very much popular, and with the maraging steel, people are using it for plastic industries. But in metal injection molding, like it's a very abrasive material, where we have used maraging steel, and we could not able to get a very good full line. So we have developed the M2 tool steel material for this convertible cooling application. And why convertible cooling applications like cooled tool inserts are very much required for the different processes like injection molding or the die casting, because of uniform mold temperatures, which because of that you can avoid a lot of defects in the components. You can get less distortion in the components, less defects, less distortion, good emission control. So you can adopt the additive manufacturing and the material combination to get a better processes, better components. So it's all integration. Again, you are using the new processes and the new materials for enhancing the existing processes and the components. So this is the binder jet M2 material which we have developed, which is almost getting the density close to 100%. Very good control on hardness. More than the regular hardness and the density, the more important what we achieve by developing the M2 tool steel by the binder jetting is the very fine grain microstructure. And because of the very fine grain microstructure, we could able to get the wears much better than the rod tool steel material. And as you know, the powder metallurgy tool steel material are also popular because of the fine grain, but we could able to get better than the commercially available tool steel M2 material, which is done through powder metallurgy. We could able to get better properties than that because we use much finer powders for the binder jetting than the powder metallurgy, and we could able to further fine tune the sintering process to get the finer grain microstructure. Because of that, we were able to significantly improve the wear resistance, which you can see in the lower left side graph. And also because of the fine grain microstructure, the machinability is increased. Because machinability of the tool steel again is a problem. So because of the fine grain microstructure, we could able to easily machine the component. So you are able to improve the machinability, the performance of the material. So you can combine many improvement by choosing the right process for processing the material. So like that, you can use this technology for many other materials by improving the properties which is not possible with the conventional laser bed fusion methods. Okay. This is the available the systems at our end. We have from X1 the machines from HP, and so we do a lot of material development on stainless steels, tungsten carbides. Now we are doing it on the nickel-based, cobalt-based alloys as well. So there are a lot of work is going on using adapting the metal binder jet fusion method for different materials apart from the standard stainless steel materials. So the next technology which we are going to talk is about the lithography-based metal manufacturing element. Like the digital PLP is where the steel lithography is very much popular in plastic, but now it has been adopted in metals as well as ceramics. We have a system for the metals. Why the lithography-based system? Now, what is the advantage? What we get here? Main advantage is getting a very fine features. We can get a micro featured components with this technology. This technology is very simple. Like you have a starting feedstock which is mixed metal powder mixed with the photopolymer, and this feedstock is normally solid at room temperature, and you have a heated plate which rolls over the where the feedstock is stored and creates a very fine layer into the building platform, and that layer again when you exposed to the particular light at the required area using PLP system, you get the localized curing of the photopolymer and making the cured layer of the component. So this process continues, so layer by layer, and then you get the component. So at the end you have similar to like you have a box of feedstock which has got a cured material and uncured material. So cured material we just heat it and remove it and take the cured component, and that cured component we wash it to remove some whatever extra material is sticking. That goes to the again debinding and sintering. So again this is the sintering based technology. So this is again the same steps what I mentioned here. So this is the system what we are having from Incus. It's a very small system with a build box of say close to 60 by 90 by 120, and presently we are processing typical stainless steel material. Also we are working on other materials as well, including copper, titanium and zirconium materials. So the tolerance, again we can go plus or minus 1 or can go up to plus or minus 1%. Minimum feature size is 0.1 millimeter, and you can get a very good surface finish area of close to 2 micron. So you can get a micro component, you can see the components, what is being held, you can see it here. These are the micro components we can really make it. Mainly these kind of components used in medical industries, especially for minimal invasive surgeries, MIS applications, very small components or any components, this where you require very micro features. So this is also one of the promising technology used for very small or near shape component with a good surface finish, which can be used. Okay, so regarding the, these are the two processes. I just wanted to know that we are working, and we can always work with the people to develop the material or evaluate the different applications what we are having. So regarding the powder, because at Indomin we are not only the component manufacturer, we are also the powder producer. We have got the gas atomized powder production, almost 2,400 tons of the capacity of powder production per year with the 3 atomizers, which we are having with the different materials. I will briefly tell about what we have. So what I will do, I will not go into the details of what emerging powder technology, because already a lot of speakers have mentioned. But I would like to quickly tell how we tailor the powder or the binder jet 3D printing. Like in binder jet 3D printing, the most important is, or any 3D printing is the powder bed density. Better the powder bed density, you have got the very dense bed structure, which helps in you're getting a dense starting the components, especially for the beamless manufacturing processes. So we have tailored the particle size distribution for the different powders. Whatever standard powders what we get, the normal distribution, we work with multimodal, bimodal particle size distributions to get a very high tab density. Basically what we are going for a very high tab density of powders, as I mentioned here. The tab density of the powder is going from 60% to 75%. So almost typically what we get 60% is the tab density for the gas-phase powder. We have gone for 75% tab density by altering the particle size distribution. So I will not go into the detail what we have done, but I will just go to the final the evaluation. So what we have done a printing of components, and one more advantage what we are seeing, we could able to increase the layer thickness almost to 1.5 times. That typically what we used to go with the standard powder, which have improved the build speed or the build speed almost close to the double. So we can improve the productivity as well. We can avoid the defects, some of the defects typically what we do. So we could able to get all the properties what typically we evaluate on the center base, like density, carbon, all the tensile properties, which is the basic property evaluations which we do. We will not go into the details because of lack of time, but I would like to mention what is the major advantage what we are getting. See, you can see here, like we in the center-based technology, the distortion during centering is a major concern. So what you can see here, we have done a simple experiment, like simply supported beam centered, and understood what is the distortion level. What we could able to see, the high tab density powders have reduced the distortion levels significantly than the standard powders. So you can reduce the centering distortion as well. So apart from improving the productivity, getting the required material properties, you can minimize the centering distortion. So centering distortion reduction means you can get the dimensional accuracy, better dimensional accuracy, minimum secondary operations or minimum finishing operations, as well as improvement in the, you can see here the centering shrinkages has reduced from 16% to 11 to 12%. So there is a drastic reduction in the centering shrinkage. So because of drastic reduction in centering shrinkage, we are able to get the good surface finish. We are able to reduce the surface roughness by 1 to 2 micron RA, making it more denser powder bed during the initial printing, and improving the distortion level, like minimizing the distortion levels. So just to conclude, apart from the beam-based, there are other non-beam-based manufacturing technique, biological 3D printing, or the LMM can be also investigated by the research institutes and the academics, as well as which is widely being adopted in the industry because of several reasons. And also we have got, and there is a lot of scope for optimizing the powders, especially the compositions and the particle size distribution. We are going to work the similar methodology for laser bed, the methods, because in laser bed method, even though the powder, the initial packing density, what we are thinking is may help in reducing the support structure. Suppose if you are able to minimize the support structure to a minimum, a lot of the post-processing operations can be avoided. So we are going to work in that direction. Maybe the next time we can present on that. But this is the work what we have done till now.
We will now start the third technical session of the day. This session has a theme of design of additive manufacturing machines. So this currently the session here, design of AM machines, is being chaired by Dr. Naganmaya, Director, Central Manufacturing Technology Institute, CMTI Bangalore, and the co-chair is Dr. Sri S. Ramesh Kumar, Scientist G, DMRL. I request Dr. A. Venugopal Rao to kindly introduce the chair and co-chair.
Good evening, ladies and gentlemen. We are now in the technical session 3A, design of AM machines. This session is chaired by Dr. Naganmaya. He is an accomplished research scientist and leader with 30 years of diverse experience in 2 national R&D institutes and industries. Currently, he is serving as the director of Central Manufacturing Technology Institute, Bangalore. He previously held the position of Chief Scientist and Head of Micro Nanosystems Technology Group at CSIR, Central Mechanical Engineering Research Institute, Durgapur, for 2 decades. He concurrently engaged as an adjunct faculty at IISc Bangalore and was an honorary professor in AESIR and IIESP during 2011-18. His academic background includes a PhD from the Indian Institute of Technology, Bombay, a master's in tool engineering from Indo-Danish Tool Room, Bangalore, and a bachelor's in mechanical engineering from Bangalore University. His research expertise covers micro nanoscale manufacturing technologies, modular reconfigurable machine tools, additive manufacturing, tool design, rapid tooling for injection molding, cost modeling, manufacturing process selection, and manufacturability evaluation. He has a publication record with over 108 research papers and holds 9 patents. He has supervised 9 PhDs, 15 MTech students, and 10 more PhD and MS scholars currently under his guidance. In addition to his research contributions, he is actively involved in national and international committees, including governing councils of technical institutions. He has received several fellowships and awards, including the Boys Cost Fellowship from DST, Raman Research Fellowship from CSIR, We Think for India Award from Prime Minister of India, and recognition as a distinguished scientist by Venus International Foundation. So he has an impressive track record of awards and achievements. He will be assisted by Mr. Ramesh Kumar, who is Scientist G at DMRL Hyderabad. He is heading the Additive Manufacturing project at DMRL. So with these few words, I request Dr. Naganmaya to take over the session.
Good evening, welcome to the third technical session on this theme 1, Additive Manufacturing Technologies.
Let me start my talk by presenting some of our work at IIT Madras, what we have been working, especially in COVID and post-COVID time. So I'm going to show first some of the success stories what we have got in Hyderabad, and then from the success stories, we learned that these relation beam shaping and real-time monitoring system are essential, especially for powder bed based additive manufacturing. So I will just touch upon first what we have done so far, and then why we are working on these beam shaping and real-time monitoring for the defense generation moving forward. So I'd like to acknowledge first to begin with, so some of my colleagues. So we collaborate extensively with Professor Saranan, who is going to give talk next in the session tomorrow on design, and then Professor Patada. And we have worked very closely with the industries. So two industries what I present over here, so Product Forge, Chennai, and Intech Additive Solutions, who are an OEM for powder bed, along with Ramesh, so what I see here. Some of the developments what we have done for them, which I'm going to present, and then some of the success stories as well. And of course, we also work extensively on medical implants, 3D printing, titanium and cobalt chrome. We collaborate extensively with the surgeons in and around Chennai and also in Hyderabad. And one startup, Zodiac's Innovation Lab, where we work with them for facial reconstructive implants by additive manufacturing. And so some of the implants what we also design and print in titanium for video plastic. And we collaborate extensively. And then I'll show some of these developments and then correlate with the beam shaping and the real-time monitoring, why they are important for addressing the end users' requirement of using additive manufacturing for their application. Right, so this slide doesn't need any introduction for this audience, but I captured the developments what we have done in IT Madras, and of course additive manufacturing, the RRR term. It was invented even before RRR TUI by Professor Danigram, so I borrowed from him. So AM, we try to get the reduce, recycle, and reuse maximized by adopting additive manufacturing. Right, if you look at these slides, what we have done in IT Madras, one of the components, what you see is aluminum, the end-use component used in automotive applications. It's a plunger primary used in the handbrake in automotive. One of the OEMs, they came to us, so to make this component, so they spent about 60% of material scrap. So they start with an aluminum rod, they machine out 60% of aluminum. So they came so much of energy and material wasted. So then we developed the parameters and then mass production strategies for these components. So then the design freedom, we all know that how we can achieve lattice structures, honeycomb structures. So those are all some of the scaffolds what we have printed. And then the extreme corner, what is over here, the implants what we have designed in IT Madras, and those are the actual images of the patients, skulls, and the implant design and printed in collaboration with the startup, Zodiac's Innovation Lab. Of course, we also work extensively on printing end-use tooling applications. So one of the images is actual forging punches. So what we have commercialized by powder bed fusion with concomitant cooling channels. So therefore, you see the advantage is already here, and it is going in the higher PR levels, especially on a powder bed based additive manufacturing. Right, so I'll show a couple of stories about the extreme left. First starting with the tooling. So what you have done in IT Madras. So if you look at the forging tooling to produce end-use automotive components, so components, what you see over here are forged in multi-stage forging. The punch, what is used in this forging application, so these are all made using H13 or M2 steel. And the life of these punches are extremely poor. Okay, so the load applied on these punches are tremendous. So in this case, what you see here is a 15-ton press used for product forge. And these punches are subject to extreme thermomechanical fatigue. The life of the punch is therefore limited, and it comes around 1 hour, and it takes about a month to make one punch. In a conventional way, if you start from say a cast billet, and then subsequently we need to anneal, and then heat treatment, punch and peppering, and then hard machining, and then again sustainability. And subsequently we make these punches, and then you see that the punch fails in within 1 hour of service. Right, so In order to enhance the life of these punches, we need to make sure that the punches are not heated up, especially in hard conform forging, so that we can mitigate the thermomechanical fatigue that is associated. You see that failure of the punch, conventionally made punch. So the best way to produce these punches with enhanced cooling efficiency is to introduce the cooling channels inside the punches. But the challenge here is whether the mechanical performance of these punches would still be meeting. Suppose if you introduce cooling channels, multiple cooling channels inside. Right, we took up this challenge of making forging punches with the cooling channels in hard to print materials like M2, in this case S13. We carried out extensive analysis of parametric development, starting from understanding the interaction of lasers with the microstructure development, and then we wanted to minimize as much as post-processing possible. So as printed condition, we achieve required hardness and the tensile properties and fatigue properties, so that we can straight away use the punch with the either sustaining or surface improvement in the end use. So of course, the design calculations are carried out to optimize the cooling channels designs. What you see here, the comparison of the punch behavior using an FEM-based simulation model and without solid cooling punches. And then punches are designed, once we design, then the optimization of heat transfer was carried out. The challenge again was here to print these punches which are about, say, 94 mm diameter with a height of around 180 mm height. And even further, if you see multiple dimensions here. So the challenge here is how do we print these objects with defect-free microstructure so that such a heavy loaded applications we still can produce or use additive manufacturing, especially for bed for this application with control cooling channels. So we could do that, then the thorough understanding of the physics of the process, how the laser material interaction takes place, and how do we minimize the defects, and how we can control the cooling rates in this process so that the microstructure is obtained as we require the end use. So we could carry out such work thanks to all the advanced techniques that are available in terms of real-time monitoring and the control over the cooling rates by mitigating the part planning strategies, for example. And this is possible only when we have the equipment which is capable of doing what we want to do. That's the reason, having our Indian OEMs, Amaze and Intech, so that we can play around our own parameters and develop for them, so that we can get such components and then further increase the efficiency of the process and then commercialization of the 3D printing. So the video what you show here is the first trial we carried out by developing the entire process chain for printing forging punch. And then we took up the trial. So now this company continuously now using additive manufacturing, and of course the various cost calculations we carried out by moving conventional to the additive manufacturing. You see here the conventional punch surveys about 2,000 to 4,000 components, and we took it in fact more than 20,000 components from 1 hour to 1 whole shift punch surveys. Okay, so tremendous amount of energy saving and material saving we look at. Now we are also working further from 40 micron layer thickness to 90 micron layer thickness, so that the punches can be produced even much faster rates. Right, so we now you see that how additive manufacturing can change the conventional manufacturing methods for cooling. We set up again the production facility for them by transferring complete technology, and this is probably the first production technology in industry where the forging toolings are continuously produced, and they have been printing now last 1.5 years close to 60 to 80 punches per week. All the forging punches what we show for hot coating are all now printed using Amaze equipment which is installed, and they are putting one more line, again production line to produce these forging toolings. So this is one of the success stories where we enjoy the commercial production achievement by again understanding the science behind what the laser beam interacts with the material, and how do we monitor the defects and how do we control the defects by carefully changing the process parameters, and some of you asked about the motor characteristics. Okay, so this is one story I wanted to share. And then the second story is about all of you are all aware how the 3D printing can help us in saving life. So a couple of example case studies I wanted to show. This slide is very close to my heart because the hospital DHS, what you see here, it is just next door to our IIT campus. And the DHS hospital, they are one of the best for neurosurgery in the world. Okay? And they also help poor patients free of cost by treating them. But biggest bottleneck for them was to get an implant, especially the implants which are really specifically required as per the anatomy of the patient. Okay, so when I went there for some other work and I saw I interacted with a neurosurgeon and he told that their operation theatre is also a workshop. Okay, because when they have a patient with an accidental trauma with skull breakage, and they could not wait for an implant to arrive very conventional manufacturing. So they somehow get a roughly shaped cutting plate, and then they literally use the cutting blades, hammers to shape the titanium plates for their patient's skull on the theatre. Okay, so and it was really touching for me, because we have the technology to produce implants on demand. So why not explore additive manufacturing? So they collaborated with them extensively. Where Saravana is going to talk about the design. So we have now the algorithms to convert the CT data from the CT data to directly an STL file, directly from patient's the MRI or CT image. So what you see here is again the process chain, and this patient surgery was carried out in June, and again so there was an issue with the accidental trauma, and he's been living like this. And there was a tremendous amount of damage already happened to his brain because of the atmospheric pressure happened. So again, so what you see here, the process chain, so we get the CT and then we segment the soft tissue to the actual bone reconstruction, and we get the defect dimensions. Once the defect dimensions are identified, so we can exactly design from the left the skull to the other right skull, what you see over here. And what is the advantage here is 3D printing, we can also use the design for lightweighting. Like what you see here in the implant, this is a titanium AS64 lattice structures. By introducing that, we also introduce offsetting property and also lightweighting. So if you make the same implant with the solid titanium, it will weigh about 152 grams. But then with the lattice structures, the implant weight is, this implant weighed about 40 to 42 grams. So this is as light as the human skull. And then, we closely work with the surgeons to get all the anchoring points right. And then on the theatre, when I went there for the surgeries, so now the doctors just take the implant and place it and screw it and close. So from 4 to 5 hours of surgery, the time of surgery is reduced to hardly an hour for such a complex surgery, because now the implants are made for the actual skull defect. Okay, so and the image what I show here is the image of the patient we have taken 2 weeks before and the CT. You see a complete recovery of the same patient, so even the growth. Right, so one more quick work what we have been doing on facial reconstruction mainly for black fungus patients. You see here this is a defective face infection. What you see here, these are the infected regions for when a patient encounters black fungus. Especially during COVID, this was a serious problem. Number of cases were recorded. You see these statistics, these times of India, and data after data wave. So close to 1.75 lakhs patients lost their face due to this black fungus, because black fungus is dreaded. So once what you see the previous image starts eating the bone, you have to remove the infected bone region to keep the patient alive. But people are living like this. Okay, so this is the same patient after the surgically removing the infected part. And then if you look at the actual patients, they don't have anything in the mouth. No teeth, no face, and I'll show one of the case studies again. And he literally lost everything and they could not eat and could speak. And they have been living like that, and most of them, they cannot afford an implant. And these implants are extremely specific. Each implant is unique. So therefore, the best way to produce those implants are by designing specifically for patient and then use additive manufacturing to print the implant. So in this case, you see that they actually implant what you designed and printed. Quickly, I'll just run through one case study because running out of time. So this patient again, so he's actually from Hyderabad. So this gentleman, and he went through hell due to the black fungus infection. So you see, due to the infection, he also lost eye actually taken out because of the entire socket is also infected. And this gentleman is living for last 2.5 years without anything. So luckily, his cousin who happened to be one of our students, and we brought him to Chennai. And then we designed the implant, and then we gave the implants. Okay, so you see, so currently, he also got his prosthesis, and we brought the smile back. So this is what additive manufacturing can do for restoring smiles for people. Okay, so now these two success stories, what you see here in medical as well as how additive manufacturing can bring success in engineering field. But then it cannot happen without understanding the science behind it. Okay, so say for example, the forging tooling what we have been working on, it has to be absolutely different field. Because the moment you have porosity or lack of fusion in the microstructure, and these are all subject to extreme loading. Okay, so immediately it may develop a pretty crack, and then the punch can fail prematurely. But then the industry will question the technology, right? So they may say that punch fails even before the conventional punch. They will say that they will not be viable for this application. So the problem here is if you don't understand the science and then adapt the technology, and then if technology or the component fails, okay, the end user will question the technology. Okay, so therefore the control of defects and the achieving the required properties first at first time and every time is important. So therefore these kind of real-time monitoring tools are extremely important. So these are some of the deconstructive implants what we have done in collaboration with the startup, Zodiac Innovation Lab. Okay, so with that, I quickly run through some of our recent work on beam shaping and why beam shaping is required, especially for some of previous speakers talk about minimizing vaporization, right? So and also improving surface finish, right? So there are a lot of limitations with respect to the beams, laser beams what we use, power distribution of the beams in Gaussian manner. Right, so the flat beam or changing the beam profile, how the power is distributed along the beam, okay, can give us much more freedom to tune the process parameter and to minimize the defects and to get right microstructures with proper properties. So what are the limitations of the existing Gaussian beam? If you look at, so some of you may be aware that if you take a conventional laser beam, and we have the power distribution. The graph will go back. So this is the conventional laser beam where we have the power distributed in the Gaussian manner, where the center would have a maximum the right photon intensity and kinetic energy, and it decays gradually in a Gaussian manner when we go out on the periphery of the beam. But if we change the energy distribution, okay, instead of Gaussian, a flat profile, that provides an advantage in terms of heating. Or we can also reduce the overall power so that vaporization can be minimized. Right? So some of the problems what we see in a Gaussian beam, okay, non-uniform energy distribution, overheating and melting vaporization, and fill time reduction, especially keyhole formation, porosity, residual stress failure. So all these things you see associated with use of Gaussian beam. And the other important problem with using Gaussian beam is more surface roughness. Some of you are aware of path growth. Okay, the SSA, the solid state centering that is happening when you do a full melting of the beam, the powder. Right, so there are multiple developments we have been working because as welding scientists when we are doing PhDs, so these are all done for laser welding. Okay, so they also apply the beam shaping from Gaussian beam to flat or vessel or donut shape the beams. For example, you see in the middle ring shaped beams are all ideal for a DRDL process where coaxial feed of wires can be effectively used for that. But then how do we implement Right, so there are multiple literatures, people are attempting all over the world and India. So yeah, when we started this work, yeah, it was impossible for us to do that. But the people have been showing, for what you see here, the microstructure with the Gaussian beam and post-surface quality, and the same sample, when is printed using a flat beam, an excellent surface, finish improvement, and we can also control the microstructure. Why? Because the melt pool shape and the power distribution in the melt pool, what you see here. Okay, so it will be entirely different. For the same average power, you may be melting in a keyhole mode with a Gaussian beam, whereas in a flat profile, so you will be melting in a conduction mode. So we can melt in faster rates with minimized keyhole-induced porosity and the coefficient. Okay, so how do you do that? Okay, so again, we need a help from the equipment manufacturers. So I cannot go and ask foreign OEM to give me an equipment where I can use all these toys. So thanks to our own colleagues sitting here in Tech and Amaze, where we can play around their equipment to introduce this technology. Right, so we have been working with Intech on introducing a beam shaper on the line, so that the pi beam shaper and beam expander, those are the two instruments we require. Pi shaper is nothing but it contains a diffraction rate, the grating which diffracts the conical beam, and then we have a prism which again creates a focal with a flat head and can be connected with the automation. And then we can, from the conical beam, we can also get the flat profile generated, and then this can also be tuned. The pi shaper can also be connected with the simple trigger, in which we can also change the beam shaping on the board. So for example, we can still use a conical beam when you are printing a large object in the middle of the layer, and the edges can be printed using like what you call the upskinning and downskinning, using a flat head beam, so that surface finish can be improved much better. Okay, so these are during the research what we got. So these are the cubes we printed using a flat profile, and you see the surface finish. Now what is interesting really is the comparison of the build rate. So when we calculated the build rate, so in a conventional Gaussian beam with the same identical density, so we can build about 3.9 mm square per second, whereas with the flat beam can print up to 8 mm square per second, mm cube per second, sorry, with the identical density with defect free. So almost like 2 times increasing in productivity, and also with excellent surface finish. So these are something for pH printed using a flat beam in our printer using the beam shaper. Okay, so you see the surface toughness, what you get, it's about 1 RA. So with the flat beam, what you get. So this is a nice success where we can also now use another variable along with the laser power, scanning speed, what we talked about, where we can also change the power distribution of the beam to tune the microstructure, or engineer the microstructure and the surface. Okay, the second work on institute melt pool monitoring. Again, knowledge is there in welding. Right? So welding, we have multiple melt pool monitoring systems, and we can understand from the laser reflection behavior, so whether a melt pool is stable or it is attracting some dissolved gases to form a blowholes, or we are also creating crack. So a simple technique we can use which can be very effective. Like for example here, so we use the reflection coming from the melt pool, okay, because the fact that all the metals and alloys they have very poor laser absorption. Now, if you use the infrared laser, that's most likely. So if you use an infrared laser, almost 70% it gets reflected. So therefore, we can make use of those reflected beams to monitor the actual the phenomena that are happening in the melt pool. Okay, so we again devised a simple, not simple, slightly complicated system where we also monitor the reflected laser intensity coming from the molten pool. Right, so we can monitor. So suppose if a reflected beam is coming, I'm using a photodiode, and that reflected beam intensity can be converted to voltage signal. If a stable melt pool is forming, we know what would be the voltage reflected coming from the reflected beam. If instantly some changes that are happening from the reflected voltage intensity, and we can calculate or we can see that something else is happening than the pure melting and the standard vaporization. Okay, so this is one of my students' MS thesis. What you see here. So the actual the ray diagram. Anyway, the idea is very simple. So we use a simple photodiode which is monitoring the reflected laser beam. If it is stable, well good. Okay, we get the voltage signal. If it is unstable from defect, then the voltage signals will tell us something else is happening other than a simple certification. Let's skip this, the actual part of it. So what is interesting here is again, we record tremendous amount of data. So what you see here, when they are printing one layer, these signals correspond to laser on. Okay, so the tremendous amount of information is there in this field where the voltage signal is changing for a build. So we can also see that something else is happening. So imagine this is printing of one layer of aluminum, let us say 10 mg, and what you see here, if you monitor the actual reflected beams, the majority of data falls in this domain. That's what you see here. But then there is also a small dip if you do a double derivative of the voltage signal as a function of data points. And you can correlate from these changing slopes the number density of data that is actually falling below this voltage. And if maximum number of data is falling below this voltage, that means that a build is of very good quality. What you see here in this example, so 98.3% of data is falling below this range, and that means that we get 98.3% of good signals. So that means that remaining could be corresponding to defect formation. That's as simple as that. So using this simple reflective based voltage measurements, so we can also now correlate the density of the component, and this can also be now used as an on-the-fly defect prediction. Right? So we got very good accuracy from this signal. And what is interesting is we can also reconstruct defects from these reflected images. So what is here for the printing of aluminum tube, and how the porosity information is captured from the reflected signals. And this is the actual tomography of the tubes what you print. So one way, if you compare, even tomography when you do slicing, this is very coarse slice. Whereas here you see the actual distribution of the porosity defects, and that is the right layer. You see here how the porosity is distributed in the signals, and which are also can be correlated with the tomography. The tomography is done 40 micron slice, for example, and this is done with much coarser slices. Okay, so these kind of techniques are important. Where suppose if you understand or if you identify that a defect is forming during printing, you can also let the laser to remelt the layer, and so that the defects can be mitigated then and there, or the feedback can be given so that the Tranta parameter can be adapted. That's what we are taking forward this. Okay, so with this, I will conclude the presentation, and I hope I have given an idea about the research going on right in Madras. We talked about DSIs and forging tooling, commercialization, beam shaping, and the defects on the market. Thank you for your attention.
Very good afternoon to all of you. There was a hiccup, I hope it will go well. Okay, the topic I am going to talk is electron beam hybrid manufacturing. We didn't know anything about electron beam about 6-7 years ago. Fortunately, we have both the partners of us. We are developing two very interesting machines. Totally 4, but 2 are strongly funded. One is about 5 crore, another is about 5.6 crore. In the 5 crore project, we are developing a powder bed fusion technology. AMS is AMAZE. AMAZE is the partner, so he's here, Dr. Vishwas is here. And we also have Mr. Anthony, who is from L&T. L&T gave a single installment, single check of 1.4 crore. And they have also given completely 1.25 crore. So that shows our industrial interactions. And let us hope that both will become commercial machines. So let me move forward. So if you like, you can shoot the page. They're not working. Selfie. On here. start with the preamble, then quickly some advantages of electron beam hybrid manufacturing. Then these are the 4 projects we are doing. The first one is powder bed fusion technology. Second one is using multi-wire cladding. Typically, when you want smaller and precise machines, you go for powder bed fusion. If you want larger component with less precision, you go for wire-based, cladding-based technology. And the third one is based on sheet metal. We want to use sheet metal as the raw material, reel of sheet metal, and then from that we want to produce. That is an internal project. Then we have also developed a new type of gun. All other systems use thermionic emission. You heat a filament and then the electrons come out. Then you apply a huge voltage, something like 60 kilovolt or 200 kilovolt. Then the electrons get sucked towards the anode. That is a typical approach. So in this, we create plasma in a chamber, and then the plasma, from the plasma we suck the electrons. So we have a proof of concept, but I will not dwell into that, there's no time. We have also developed our own power supply systems. These power supplies, extremely high voltage, minus 60 kV is the difference between cathode and anode. So developing them, then on to that you also connect the filament power supply and grid power supply. So isolation becomes a problem. So you have on one side very high voltage, on the other side as low as 2 volt. The filament gets heated in just 2 volt power. So you need to isolate them if you need to control. That becomes challenging. So these power supplies cost anywhere from 60 lakh to 1 crore. And we were able to develop a vendor locally who was able to give in a tenth of the price. Finally, we ended up paying him only 7 lakh. He was able to produce. That's the claim I have been making. Okay, so this is the slide talking about our style of working. I work in 2 major areas. One I call as hybrid manufacturing. It's for the last 30 years we have done a lot of interesting work. The second important area which I started in 2005 is a drone. We are the first to develop drone in the country. It was in 2005. Subsequently, very recently on April 10th, I flew a drone where I was sitting and piloting. It's a big one, 1 meter diameter rotor. So that's the next area I'm working. So our ambition is to develop as an ambulance. So other things they have already read during the introduction. Okay. Does it run? Or yeah, this is the drone. It's a single seater drone. About 2 minutes video we can tolerate. I went up to 60-meter height. This is our playground. A lot of dust gets generated, so we put a mat of 15 meter by 15 meter. So the idea is to use it on terraces. The ambulance will land in the terrace of the house where the patient is there. It will pick him up and then it will fly in a straight line, drop him to the hospital's terrace. So the hospital is a hospital. You can see some of the innovations. Football is our landing gear. Some more hospital. Yes. Some more. Some more. You can see the dust it can create from that height itself. That's what he said as dare with care. Okay, you can go back. This is the ambulance concept. Don't worry about the structure. Look at it as only a chassis of a truck. You can give enough protection and other covering surfaces. The blade is going to be 62-inch carbon fiber blades. This will be a 3-seater, patient will be in the middle, and on either side will have the pilot and the nurse. Oh. Can you change? I will tell you change. Yeah. We'll move on. Next. I think this introduction is already known. Next. Yeah. So this also we can skip for the sake of time. Skip it. Yeah. So I think you are all familiar with the picture tube, olden day TV, CRT, cathode ray tube. In fact, cathode ray and our electron beam are the same. Okay. So the picture tube, if you turn 90 degrees, that is nothing but our electron beam welding or electron beam additive manufacturing or even our SEM. Okay. So if you look at the net part of it, that is what is shown there. So you have a cathode which when you heat it to 2000 degrees centigrade, tantalum is typically used. You get a lot of electrons accumulating there. They don't have velocity at that time. So between the anode and the cathode, we apply 60 kV. You can go up to even 200 kV. So the electrons get accelerated. By the time they reach an anode, they reach about 60% of the light velocity. The anode has a central hole of about 4 mm. So the electrons pass through, some electrons do hit the anode, so we have also a cooling arrangement on the anode. Then you see the first cylinder there, that is a focusing cylinder. So magnetically the electrons are focused into something like 0.3 to 1 millimeter diameter. After that it comes in a focused condition. Then we have multiple sets of coils. Typically we will have 2 pairs of coils, one for X direction, another for Y direction. This is a deflection system. So when you apply voltage just to these coils, you can position it anywhere on the table of your interest. So because see here you have ionization taking place. Whereas there it is not ionization. Electrons come out because of heating the filament, and then you give acceleration potential to pull the electrons towards the anode and then work there. So the principles are different. Here it is ionization based, there it is thermionic emission based. So I am going to compare it quickly based on these 5 parameters. The pressure, the voltage, current, the gap between the electrode and the table, then the diameter of the beam. So here, as you know, it's a low voltage, high current system. You approximate about 100 volt will be the welding voltage for the arc. Whereas the current would be anywhere from 400 to 1200, 1500 ampere. Whereas there, since the voltage is very high, if our machine is 12 kilowatt, we will have only 200 milliamperes of current. So this is a low voltage, high current system. That is a high voltage, low current system. And here the operation happens in atmosphere. Here it has to happen in high vacuum. The vacuum is of the order of 10 power minus 4 millibar. And in the neck area, it should be around 10 power minus 6 millibar. So it's extremely high vacuum because we don't want any particles, air particles or organ particles to be there. Then they will affect the beam movement. So you need extremely high vacuum. Therefore, the electron beam system is typically enjoying or suffering 3 extreme V's. Okay, high vacuum, high velocity, and then high voltage. Okay, all the challenges in electron beam system arises out of this. Next, please. Okay, here I have given a comparison. Will not go through the entire thing. According to me, the second point is the most important advantage. Extremely high scanning speed. The scanning speed in laser, your scanning speed is of the order of 10 meter per second, and in typical metal powder bed technologies, they use about 2 meter per second because the scanning is done only once. During that full scanning, the powder bed should cross the sintering temperature. Therefore, your scanning velocities are the order of 2 meter per second. Whereas in electron beam, since there is no inertia, no mirror moving, only the electric current flows on the coil, you can reach 10 power 4, 10,000 meter per second velocity. And in SEM, your speeds are 1 lakh meter per second. According to me, more than velocity, acceleration is important. Okay, so the acceleration possible on any laser scanner is about 7,000 G, 70,000 meter per second square. Whereas here it is close to infinity because the current flows in the coil at almost light velocity. Therefore, you can get that kind of acceleration. Instantaneously, you will be able to change. That is the most important advantage. That is very much applicable only for powder bed fusion technology. It's not applicable for cladding technology where physical movement are involved. So when you can scan it, imagine that you have a powder bed, you want to scan a circular area by several rasters and a circular loop. That movement will take place at 10,000 meters per second. That means each layer you can scan in milliseconds. Okay? But then you don't get enough temperature. But the entire circular area is uniformly rising in temperature every time. Every time it is 0.1 degree centigrade, 0.2 degree centigrade. So you keep on doing the scan, repeat the scan till you cross the sintering temperature. So instead of doing one single scan and put the bed into inhomogeneous temperature, it's more like flashes in the camera. Every time it's a flash, therefore the temperature rises very uniform. That means electron beam system of the powder bed fusion technology will not suffer any residual stresses because residual stresses arise out of temperature differential. So when you don't have the temperature differential, it will be free from residual stresses. That is what I will put it as the first advantage. Although for the sake of funding agency, we will say that high energy efficiency. Energy efficiency of order of 95%, whereas the laser very often it may be 10 to 15%. Rarely they reach 40%. Okay, vacuum is another advantage, but it was a limitation in the past. That's why deterring people to go to electron beam. But today we have very affordable and efficient pumping systems. Therefore, it is no longer a drawback. Instead, it has become an advantage because you have a really inert environment. Even if you use the organ particles may get embedded into the gap in the powder bed. Whereas here it is totally free. So I'll say that the inert atmosphere is really inert in the case of electron beam system. And there are a few other advantages we will not bother. Next. Okay, so these are all our projects. I already mentioned, first is powder bed fusion, second is the multi-wire system. First is supported by AMD Bangalore, 25% from the government gave 75%. In the case of DST project, DST gave 75% and L&D gave 25%, about 1.4 crore. Okay, we will first talk about the powder bed fusion technology. Next please. Okay, so we will talk about the shape design. Typically, we are going to put motion systems inside. So we designed a rectangular box as our system. But ideally, if you ask a mechanics expert, he would prefer spherical geometry. Okay. Next best is cylindrical geometry. Box is the last. Then you need to put a lot of range. Your thickness will be very high. Next, please. So the next point is about the ribs, where the ribs should be. In case of a pressure vessels, ribs should be outside. In case of vacuum systems, ribs should be inside. According to me, designing a vacuum chamber is far more simpler than a pressure vessel, because pressure vessel like hydrogen tanks and all, they store at something like 300 to 1000 bar, whereas here at best you suffer only 1 bar. Therefore, your forces are limited to that much, and in case of any accident, here it will be implosion, whereas in a pressure vessel it will be an explosion. So vacuum-based systems are, according to me, safer. Next. Okay, this is about whether we should use mild steel or stainless steel, whether we should go for castings or we should go for a fabricated system. So the gas leaks. At this type of high vacuum, the gas leaks through the outside to the inside. Okay, so people normally go for stainless steel. So we also wanted, our first machine for powder bed was totally out of stainless steel, and the second machine we wanted to make out of mild steel. Try it. If it doesn't withstand, then we want to give some kind of chrome coating and all. But our partner said the first version, let us go for the normal stainless steel. So we will try it next time. Next please. This is a comparison quickly about casting as well as fabrication. We struggled to develop through UCAM a rotary table which was completely out of fabricated structure, costing about 15 lakh more than the normal table they have. So next version will go for casting based rotary table. Next please. Yeah, this is the machine. It was fabricated by Hindustan Hyderabad from here in Pina. So what you see here is all the cluster of the vacuum pumps. There are some different types of pumps. How do I do? 5 minutes only. Okay. So this is the system we made. You see at the top, that is the huge vacuum, electron gun, 1.4 meter, and weight was about 140 kg. So we had to fix it. Next please. We have to move faster now. In this machine, we introduced scissor kinematic, which is unique. Then the moment we introduced scissor kinematics, it was a circular table. Next please. See whether the video, next. Next. Yeah, video doesn't run, it may not run, video may not run, but you know how those are made. Okay? So we adopted this approach. We developed a sand 3D printer where we spread the sand, we drop the required amount of sand using a dispenser, exact rotation, and you will get exact amount of sand. And then we spread in a spiral way. It works very fine. And the same thing we adopted for our metal machine also. Next. Next please. Go back. Okay, this is a various methods of coil, how to manufacture the coil. This is the coil that is found in the picture tube. Then we were exploring various other coils. Finally, we decided on this coil. We are also developing indigenous in the high voltage, not high voltage, high speed. That's about 100 kilohertz will be the speed of the power supply. We are getting fabricated in Mumbai. Next. Now I am coming to our next machine, which is the multi-wire cladding based system. As I said, this is for larger machine. The machine has more than 600 mm work envelope, and height can be up to 600 to 700. This is what we developed. The wall thickness on this rectangular chamber was almost 30 millimeters. Okay, then for the last 2 years, we were reviewing, redesigning, improving. We were very proud of the system, but then my collaborator said, I want you to meet one expert who is in pressure vessel design. Next please. That guy completely rejected our rectangular box design. He said, you are not taking advantage of hoop stress, so you must go for spherical shape or cylindrical shape. Finally, I bargained and went for cylindrical shape. Then Dr. Ramani, who is our guru in Ahmedabad, he gave some advices. We removed a Castrol tank which was in this. By the way, this design we obtained from DRDL for a technology transfer. Okay, this is their design. So Dr. Ramani said we don't need a Castrol tank. Then we also don't need an isolation valve. So our new design works without all that. So 1.4 meter, 1.3 meter becomes 400 mm in length. 140 kg becomes 40 kg. So we were able to move it. Okay, next please. Then the question came, having gone to the cylindrical design with dome at the top and bottom, what about the door? So Dr. Ramani said, no need for a separate door, just split it. And that guy said, don't split like this, split like this. I didn't understand why he said. Then we took about some time to understand. Next please. Yeah. So the reason is, the lower end will be used for loading and unloading. The upper end, the duct which is required as the inlet for vacuum pump is about 500 mm. Therefore, it has to be tall. Then we said, we anyway will have motion system. The slides of the motion system itself will act as a slide for the door. Okay, so next please. Yeah, so this is how we decided to make it. We also wanted to put the same motor to lift it, but the height became very high. So we'll put a lifting cylinder at the outside. Next please. This is a machine we have fabricated. My model is very simple. We locate an expert, irrespective of whether we know or not, and then we hire a house there. we put 2 students there. I visit every week, we place order on them. No, we have given almost 2 crore order to the company. So this is the mission. These boys, my PhD students, they are living there for the last 2 years. So they will complete. As soon as the project will be over, they will also submit their thesis and defend their thesis. Next please. So the motion system has already reached 2 days ago. It was under development in Mumbai. It has gone to Ahmedabad. So we are integrating it now. By December we have to complete the project. That's the deadline. Next. Yeah, this is our multi-wire system. We'll have 2 spools on which 4 sets of wires will be. Now these wires can be of same diameter, different diameter, same material, different material. That means it gives you the opportunity and infrastructure using which you can do heterogeneous matrix manufacturing. Otherwise today we don't have any infrastructure in which heterogeneous matrix can be manufactured. So we primarily intended this design because we wanted omnidirectionality. The property should be same in all directions. So we went for next please. This is the machine which we initially fabricated for TIC. We proved it on TIC. Now we will have 2 more. One is already fabricated for electron beam. One more over. One more is for laser. Third is for the electron beam. Please next please. This is the initial experiment. It's a video. It doesn't work. Next. Next please. This is the power supply we got to develop. For the first machine, we bought it from other vendors, including an imported high voltage power supply. We spent about 70 to 80 lakh on that system. Then I located another guru in Mumbai, who is an electrical expert. He is only 82 years old. He is running a company called NG Solar. He fabricated. So he told me, Professor Karnakaran, it will cost at least 3 lakhs because most of these power supplies have been only 50,000 maximum order. So he said it will cost at least 3 lakhs. I was literally laughing. I said, sir, please do whatever you make, anything, burn any number of transformers, I don't care. So finally, it went a little bit beyond 3 lakhs, we paid them 7 lakhs. Still, the ratio of 1/10 is coming in as they read in my resume. Next please. Then we did another very interesting thing. I don't know how much you will be able to appreciate. I told you that there are 3 important power supplies. High voltage power supply, which is 60 kV, even 200 kV. At one end of it, the filament is connected to it. Okay, but the filament is actually a low voltage system. You need maximum 10 or 5 volt and current is about 50 ampere. Okay, but then you need to control the current. You need to control it. Okay, so you cannot interfere because one end is at such a high potential, you will get a jolt. So one has to have isolation transformer and all that. And as you saw, I am also working in drone. In drone, we use battery on the drone, and we have a joystick in a radio control, and then we use that to control the voltage supply. We adopted the same concept and we developed a system. Battery will be heating the filament. The battery voltage will be remotely controlled by our system. So our boys have developed it. Currently it is not handling that much of current. We are rectifying it. This will be a real revolution because that power supply alone costs about 2 lakhs. So this can be made in about 5,000 rupees. Next. Next please. Yeah. So I'll conclude. I strongly feel that electron beam has far more advantages than laser. Maybe I'm too emotionally attached to it, but I'm saying electron beam has more advantages than laser. So in future, I feel that lasers will limit themselves to only non-metals, and electron beam will find applications in all other metallic applications. As I said, we have 4 processes happening. We have added some of the innovations. As my claim is 2 things. One is indigenization, other is innovation. By doing these 2 nicely, we will be able to cut the price by 10. And we have demonstrated in a few things, and I have the partners sitting here. So that is a proof that the machine is likely to reach the industry. So with this I can. Thank you very much.
Good evening all of you. First of all, I'd like to take this opportunity to thank the organizers of the event for giving me an opportunity to come and present our little work here. I promise you I'll keep it short. I know I'm keeping you from the next exciting session that's coming up. So here we present our perspective coming from an OEM. We heard one industry speaker earlier. Now we'll share some of our work in terms of what is. So quick run through the topics that we'll be talking. Different perspectives about defense manufacturing and specifically for additive. Some challenges in machine building, what we've been into, some recommendations for work together. So now coming to additive manufacturing for defense, we'll look at some statistics here. India versus global. So when you actually look at metal AM systems, this is again a published report in terms of how the consumption of metal systems have been happening in these past years. So you can see the graph growing mostly, but it has taken a downturn in the COVID times. So if you actually look at some of the statistics, India stands fifth in terms of global manufacturing output at about 3% of the global consumption of manufacturing or production is what India contributes, whereas which equates to about $560 billion, while the global manufacturing stands at about $13 trillion. Whereas coming to additive as a market, globally the size of additive is about $18 to $20 billion, and the projected growth is about $50 billion by 2030. US, Germany, China, Japan are the leaders in the adoption of additive manufacturing. Now coming to the adoption of additive in India, we stand at about 0.6% of the global size. While we are at about 3% of the global manufacturing adoption, whereas when it comes to additive, we are at an abysmally small number. So nevertheless, we are at a fast growing rate. We are growing at about 35 to 40%. In the next 7 to 8 years, we are likely to catch up to some of the other countries. Globally, what is happening is in terms of investments, very high levels of work happening in terms of R&D, government policies, industrial scale adoption from heavy industries of additive is happening right now. A lot of end-use production happening, a lot of advanced materials that are being developed, and large-scale industrial additive manufacturing is what is happening. Now, when you look at India, currently the large consumers are aerospace, defense, automotive, healthcare, and tooling. We saw a lot of cases earlier today, throughout the day. We'll look at some more now. So now, some of the key drivers for adoption of additive in Indian defense. Indigenous manufacturing of the technology and self-reliance. This is what is causing. We see a lot of PLI schemes that have come up. Local manufacturing of critical defense parts, lightweighted parts, complex designs, intricate complex parts are being made, especially for things like design systems. On-demand manufacturing of customized parts. This is something very interesting, especially for obsolete parts, legacy parts for equipment. Rapid prototyping and production of prototype generation of end-use parts with shorter lead time. And finally, of course, for the Indian Armed Forces, MRO repair applications is something very interesting. DRDL and ISRO are working on not only prototyping but also batch production of some of their end-use parts. Now, we ran a survey sometime back to find out the market and the market size, and this is what came out. So basically, out of the entire volume of machines that are in the installed base in India, 33% of the entire industry is aerospace and defense. Right? We speak about metal printing here. Then we have the others in a decreasing order, as you can see, industry, oil and gas, which includes industries like oil and gas and others. Automotive is about 12, and other sunrise sectors are smaller. So this is just giving you an idea as to how the segregation of the market is. So defense is already a leader, but we believe it's still just the tip of the iceberg. There's a lot more that can be done together in the country. So in this, again, corporates are the larger ones. Larger organizations are the ones who are mostly investing in metal 3D printing, largely because of the cost that is involved in the whole equipment here. Now, another interesting perspective that came up is the growth that we're seeing. As we said, the 40% growth, what we are today to what we're likely to be is going to be 40% growth. So again, you can see the CAGR is 40% has been identified, and the sunrise sectors are the ones that are being considered as a faster growing one, which is at about 52% CAGR by about 2029, financial year 29. Is the projection that has been done. So you can see that aerospace and defense also is going to be growing faster at about 33% annual growth rate. So these are some statistics just to give you a flavor of where we stand today in terms of the adoption in the country. Now, the idea is there is a strong need to understand the expectations of defense manufacturers here in the country and provide solutions around that from additive manufacturing. So this is just to establish the why we are doing what we are doing. Now, coming to our own journey of additive, a quick introduction. We basically come from machine building background. We've been making CNC machines for 45, nearly 50 years. We go by different brands. I'll skip them, but we are largely known as the ACE group, ACE Micromatic group. We are known for machine building over, we have an installed base of over 90,000 CNC machines in and around, outside the country. We started off in a small garage in the 70s, and today completely Indian developed, Indian made, homegrown technology. Today machines all around the world. So that's what we are. Our company, Amaze Solutions, is basically a subsidiary of the parent company, the ACE Designers Group. Jokingly we say additive manufacturing from the ACE Group. So Amaze is what we are. So coming to metal printing, so we work on multiple technologies as a group, powder bed fusion, laser-based powder bed fusion, electron beam machines. Sir has already introduced the electron beam machines. We also work on wire arc PET, directed energy deposition, but for today's discussions I'm limiting it purely for on laser powder bed fusion and our journey in this whole process. Now, when we started, a lot of design work has gone in terms of understanding, screening of parts, finding out suitability of the technology for different applications. So a lot of design for additive manufacturing. Printing of parts today in our journey, we've printed over nearly a couple of lakhs of parts, metal parts, which are all being put to different industrial use in various sectors. We've enabled production, which means we've taken it from just prototyping small batch to in many areas, mass production also. And of course, we've understood materials, which is the key essence of the whole aspect. And we've indigenously developed multiple machines. Today we have batteries of these machines that we've developed of different sizes for different applications, and we've been making them in India, in Bangalore, for again multiple sectors. One of the key aspects that has been driving us is our approach. Traditionally when this technology evolved, it was largely for the top end of the pyramid, which is your medical and the space applications. But India is a large, small-scale industry, so this is a white elephant which has always been deemed as unaffordable, untouchable, additive manufacturing, especially the metal. So our idea was, how do we make it more available, affordable, and accessible? So that's our main idea. So when you look at actually comparison from conventional manufacturing to metal printing, normally it's anywhere between 15 to 20x. So our goal was to see what can we do to minimize that to at least about 1.5x. We've done a lot of things in terms of volume, laser power, layer thickness, and of course we've also worked on unconventional powders. We've heard a lot about materials, powders, the morphology, the powder structure. So we've also done things, one of course for the industry which needs very high quality of parts. That is something that continues, which will come to that. But we're also working on areas where people may not need something as dense as a 99.9%, but something as small as 97, 98%, which may be sufficient. So we worked on water atomized powder, which can come at a fraction of the cost of gas atomized powders. We worked on different types of particle sizes so that they can be more affordable, as close as ground or milled powders, or just plain water atomized powders. So the goal is to actually take it from, the paint to a white elephant grade. So that's what we say that. So make it more affordable, as I said earlier. Now, a quick run through our capabilities in terms of what we have done. A whole lot of applications from automotive, be it prototyping or small batches for different industries. So these are some of the examples that have been done in various materials. A lot of work in defense and space. Some of them may be familiar, be it nozzles for space applications, waveguide antenna for defense application, including the very prestigious national emblem that we printed for Chandrayaan, which is laid to print on the moon surface now. So these are just some of them that we've done for the industry. So we've also ventured into doing something, where we offer end-to-end solutions. When we say end-to-end, we've worked with defense industries where they have legacy parts, like what you see on the top left corner here, where an original part is taken. We go about creating the entire digital twin or the data set for it by scanning it and creating the entire 3D model. We've gone about identifying the material that's there, because these are either a Russian part or a European part which they have no history about. So we've gone about identifying material, strength, properties, all of that, creating the entire data set, then actually go about manufacturing them, 3D print them, and then finish them and give it to them. So this is something that we've given as that is demonstrating the end-to-end capability of what we've been doing. So not just reverse engineering, but also something like lightweighting, where we've taken an existing part and made it really lightweight, so it not only is more cost effective, but can also add a lot of value from its weight itself. So like this, plenty of parts done for different applications. So you can see these are the pairs have been demonstrated here for a specific military application that we've done. So we've done a bit of medical also. Murugan sir has already shared some of them, like these, where a lot of cranial, maxillofacial, mandible, hip joints, femoral joints, tibial joints. Many parts have been printed and given to customers around. So these are just a summary. As I said, we can go on for hours together in terms of what we've printed for end applications, but just to put it all together in terms of what our capability in printing and what we've been doing, and all of them are actual industrial applications which have been put to very strenuous actual cases. So presented a forging application. We believe that's like the epitome of what metal printing can do, something that never has been done before. Through good collaboration, we've been able to demonstrate how our end customer is producing them on a continuous basis for a forging punch die, and now looking at replicating that for various other applications too. All that wouldn't have happened without collaboration with academia. So two of our good partners are here, Professor Karunakaran and Professor Murugan, and many others, including Indian Institute of Science. We worked with Aachen University, IIT Guwahati, and many others in and outside the country. So we strongly believe technology development cannot happen in silos. We have to come together, we have to collaborate together to make it happen. So coming to design and development of equipment. So our approach has been trying to maintain a very innovative mindset. We've tried to see how we can do continuous R&D. We come from a technology-driven company. A lot of interactions with end customers. We've found out what pain points customers had, what were the challenges. We learned from competition and we understood what could be those gaps that could be filled. Productivity seemed to be a large challenge, so we tried to work on them. Smart interfaces, there was a need, and all the learnings from having built machines. We understood microns, we understood machining, we understood how to integrate equipment, so all that came in handy for us. And what came out was our machine. We call it a Stellar 400, STLR 400. So we offer it with high productivity solutions, high productivity features, many patented features on them, especially addressing the productivity aspect without compromising on the quality or reliability on the equipment. The equipment comes with a lot of smart features, including AI-based predictive analytics that have been built into it. So we have in-situ inspection, we have powder management, diagnostics, a very smart interface which has been developed by our team. Largely, they're like a digital cockpit where the color coding is involved, so that operators find it very useful when they're operating or using these equipment. You can see an example of what was printed in Corel in a very short duration of time for a space application. This is right here in DRDL. We've been very fortunate to be one of the, DRDL is one of our very prestigious customers, and we have this machine. This is when Ramesh sir was inaugurating the machine right here in this facility, and this again was used for very key application. It took us a lot of time to demonstrate our capability. When that challenge was put to us, we worked with the team to show how we could be as good, if not better, than our international competitors. So we also have a machine installed in ISRO VSSC, where our machines are being used for very interesting parts, rocket and satellite parts. This is the team who's owning it and running the machine there. These are some of the parts which could be displayed. So this just goes to show you the capability from size and the component challenge. I'm sure you'll be able to see the perforation in this mesh design. This is actually an actual space application part which is currently being validated. Once done, it will lead to a lot of import substitution which is currently being imported. I'm sure you can see the tensile coupon on the other side of this mesh design there in that image. So just trying to show you the capability of Indian manufacturing, Indian equipment manufacturing here. So these are very strenuous material like Ethernet 718. We've established more than 23 types of materials now, and the process is going on, the journey is going on. We've also received appreciation from both DRDO and ISRO VSSC about the product and our capability and our service. So we'll skip that. Now, coming to challenges in additive. So when we started, we had no clue about this subject. There was no one to guide us, no one to support us. If it was a gear cutting machine, if it was another existing technology, we had people who could support us, but we had to fend for ourselves. So there was no expertise available in India, especially. The subject itself is a multi-physics problem. It's not, it cannot be seen in isolation. We had a lot of combination of these that had to be addressed. We assumed that it could be more straightforward, but we had many challenges that we had to overcome, especially when we had to look at things like sensors, actuators, and get them to work together, and calibration of some of them, and especially the software aspect of it. We found ways of doing things around. We'll look at that. And as I said, multi-physics, gas flows, key challenge in terms of getting it right to make sure we get the laminar flow, to get just enough to remove the spatters from the whole printing process and not pull out powder, because that's again a very key aspect. Ensuring we get the right laser spots and the optics validated, that also was a key aspect that we found as a challenge. Getting the software right for the whole solution, because it's not easy. Though we are software, India is a big software developer. People don't know much about this software, so it needed a lot of developmental work. We had to work on it from threadbare to understand how we can have it very strong. So, interface between multiple systems. You have your filtration systems, you have your pumps and other aspects. All these were challenges because they cannot be looked at in isolation. They had to be looked at in tandem. So. All these were key challenges, including gas leakages. Though we make equipment, but nothing that could take gas leakage issues, address them. So all those had to be addressed. So many of these. So you can see those are our first set of melting that we did when we started in terms of laser in touching the powder and what we got out of it. So that's not a normal one. These are only the challenging aspects that we have shown you here. So. So then we went ahead and did a lot of other work. So choice of material identification for structural parts, trying to understand how do we, what do we do in terms of the treatment. Again, powder flowing. We had many cases where powders just wouldn't flow. Getting the applications right. Again, though people had application expertise, getting to understand what would work, what application, that was a challenge. Getting the programming aspect of it encrypted, decrypted. Controllers for this specific application, process monitoring, especially to ensure that we're printing right. All these were some of them. Intellectual property, there are many patents that are there from some of the Western competition that we've had. So ensuring that we don't infringe them, that was another Herculean task that we had to face. And of course, fine-tuning them to get that quality right. So these were some of the key challenges that we faced in our process of machine building in these years. And of course, our approach to solving these, a lot of trial and error, which we had to do when we started. And we create a lot of experimental setups, test kits to ensure we test, validate subsystems, a lot of systematic design of experiments that we had to do, single track experiments for material development, a lot of microstructural analysis to get it right, to ensure that we balance all the properties to get the whole thing right, simulations for build and ensuring the analysis goes right. And of course, learning from the group companies to ensure the geometries, all the mechanical elements can do what they're supposed to do. So all those were some of the learnings that we had. And of course, as I said, a lot of collaboration with academia, it is very team support. We work with other types of industries to see how we can overcome some of these challenges. So, and of course, exhaustive set of customer trials we did. We've had our lion's share of failures. We have a big rack of failed parts in our facility, which we don't show, and we've not put it up here just to tell you how we've cracked. Even the punches that sir said, we've probably had over 40, 50 punches which just cracked initially, and till we got the whole recipe right for getting H13 printing, and today it's a production technology. So this is how we've gone about doing it, largely because of collaboration. And of course, not to miss out on our Indian Jugaad, which we've done to get the solution right. So this is just the printing of the equipment where you can see the printing process going on. That's the printing process, that's the finished part that we have. Now just on a concluding aspect, we see a lot of, what we suggest, what we recommend to the industry and to the organizing team here to see how, what we can do together to grow this market and to grow this technology here. We need to provide a strategic focus for additive. Additive is still least in our, probably behind in our priority, whereas if you see US, UK, Germany, China, they have additive as a very strategic focus, which is why a lot of manufacturing happening around this, a lot of OEMs. In fact, in India, we have 2 machine builders, as we spoke. In China, we have more than 60 machine builders from metal alone. I'm not even touching plastics. So like that, we need some support here to see how, we had one of the speakers who also recommended this, now create a national level common platform. We see a lot of interesting work. We saw excellent presentations by different departments. If we can come together and we can post challenges, find solutions together, I think we are better off. We urge defense organizations to start collaborating with OEMs, academia, and extensively develop applications to see how we can shed some of our inhibitions that we have about the technology and how we can localize the whole technology of manufacturing in India, specifically for additive applications. Let's incubate talent. There are a lot of interesting companies, people interested in developing them locally. Let's see how we can do that together. Finally, let's invest in local development, build self-reliance, self-competence. We believe that's the only way that we can develop India and make it a very strong defense and defense additive manufacturing company. I thank you again for the opportunity.